Mars, the fourth planet from the Sun, has long been a beacon of fascination for humanity. Its presence in the night sky, glowing faintly with a reddish hue, has sparked curiosity and inspired stories across cultures and centuries. Known as the Roman god of war, Mars has been associated with strength, mystery, and even fear. But beyond mythology, this distant world holds a unique place in our solar system, both familiar and profoundly alien. Its rusty surface, shaped by billions of years of cosmic forces, beckons us to unravel its secrets. To understand Mars is to embark on a journey through space and time, uncovering not only the mysteries of another planet, but also insights into the origins of our own. Mars's reddish-orange appearance, visible even to the naked eye, is caused by iron oxide, essentially rust, coating its surface. This distinctive color sets it apart from other planets and makes it immediately recognizable, even in amateur telescopes. Its surface is a vast and varied landscape, with smooth plains in the north and rugged, cratered highlands in the south. These regions tell the story of a planet divided, shaped by contrasting forces of volcanic activity and ancient impacts. The northern plains, thought to have been smoothed by lava flows or erosion, stand in stark contrast to the southern highlands, which bear the scars of countless collisions with asteroids and comets. At its poles, Mars reveals another of its striking features: shimmering ice caps. These frozen expanses, composed of water ice and carbon dioxide, change with the seasons, growing during the frigid Martian winters and receding as summer approaches. Layered deposits within the caps contain a record of Mars's climatic history, much like tree rings or ice cores on Earth. They hint at periods when Mars's environment may have been warmer and wetter, offering tantalizing clues about the planet's past. Mars is also home to some of the most dramatic features in the solar system. Olympus Mons, a colossal shield volcano, rises 21 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. This towering giant is so massive that its base spans the width of France, and its gentle slopes suggest that it was built by long kilometers. Near the equator lies Valles Marineris, a canyon system so vast that it dwarfs the Grand Canyon. Stretching over 4,000 kilometers, it is a deep scar on Mars's surface, carved by tectonic forces and erosion over eons. These landmarks are not just geological marvels. They are reminders of a time when Mars was a world of immense volcanic and tectonic activity, a planet alive with forces now long dormant. Despite its serene appearance today, Mars' surface is anything but static. Dust storms frequently sweep across the planet, sometimes growing to engulf it entirely. These storms, driven by winds that can reach speeds of over 100 kilometers per hour, lift fine particles of dust into the thin atmosphere, creating a reddish haze that can last for weeks. While these storms are a challenge for exploration, they are also a reminder of the dynamic processes still at work on Mars. Beneath the dust, the planet's surface retains a haunting beauty, with rocks sculpted by wind and traces of ancient water etched into the landscape. Compared to Earth, Mars is a small world, with a diameter of just over 6,700 kilometers, about half the size of our own planet. Its gravity is much weaker, only about 38% of what we experience on Earth. This reduced gravity would allow future explorers to leap great distances and carry heavy loads with ease, but it also poses challenges for long-term habitation. Prolonged exposure to low gravity can affect bone density, muscle strength, and even the cardiovascular system, issues that researchers are already studying in preparation for human missions to Mars. Mars's orbit around the Sun is another feature that sets it apart. Circling our star at an average distance of 228 million kilometers, It is located in a region sometimes called the cold desert zone. This distance makes Mars far colder than Earth, with surface temperatures that can plummet to -125 degrees Celsius at night. However, its orbit is not perfectly circular, and this slight eccentricity leads to noticeable variations in its seasons. Southern summers, for example, are shorter and hotter than northern ones, a quirk that adds to the complexity of Mars's climate. A Martian year is nearly twice as long as an Earth year, lasting 687 days, while its day, called a sol, is just 37 minutes longer than a day on Earth. This similarity in day length could make the transition to life on Mars easier for future settlers, reducing the strain on their internal clocks. Mars is also a familiar visitor to Earth's night sky. Every 26 months, during an event known as opposition, Mars and Earth align their orbits, bringing the two planets closer together. At these times, Mars becomes especially bright and prominent, capturing the attention of stargazers around the world. Historically, these close approaches have marked key moments in our exploration of the red planet, from the first telescopic observations to the launches of robotic missions. The brightness of Mars during these oppositions has fueled both scientific curiosity and imaginative speculation, turning the planet into a symbol of discovery and possibility. As a neighbor, Mars is uniquely accessible compared to other planets. At its closest, it is a mere 54 million kilometers away, a vast distance by human standards, but relatively small on a cosmic scale. This proximity has made Mars a prime target for exploration, with missions ranging from orbiters and landers to sophisticated rovers. Unlike Venus, with its thick, hostile atmosphere, Mars presents an environment that is challenging but not insurmountable, a place where science and ingenuity can push the boundaries of what is possible. Orbiting Mars are two small moons, Phobos and Deimos, whose origins remain a subject of scientific debate. These moons, irregular in shape and resembling captured asteroids, are both fascinating and mysterious. Phobos, the larger of the two, orbits so closely to Mars that it appears to race across the sky, rising and setting multiple times in a single day. Its surface is marked by grooves and craters, the largest of which, Stickney Crater, hints at a violent past. Deimos, more distant and smoother, moves more slowly across the Martian sky, a faint and steady companion. These moons are not just scientific curiosities, they could also play a role in future exploration, serving as bases or sources of raw materials for missions to Mars and beyond. Despite its proximity and similarities to Earth, Mars is a hostile world. Its atmosphere, composed mostly of carbon dioxide, is thin and unbreathable, with a surface pressure less than 1% of Earth's. This thin atmosphere also provides little protection from cosmic radiation, exposing the surface to harmful particles from the sun and beyond. Temperatures on Mars are extreme, ranging from a relatively mild 20 degrees Celsius during the day to a frigid 125 degrees Celsius at night. These conditions make Mars a challenging environment for life as we know it, yet its history suggests that it may have been more hospitable in the past. For all its differences, Mars shares key characteristics with Earth that fuel our fascination. Its seasons, axial tilt, and evidence of ancient water make it a planet that feels familiar, even as it remains profoundly alien. The traces of rivers, lakes, and even potential oceans etched into its surface tell the story of a world that may once have harbored life. These discoveries inspire hope that Mars could one day be a second home for humanity, a place where we might expand our horizons and ensure our survival as a species. Mars is not just a planet, it is a symbol of possibility. It is a reminder of Earth's fragility and a challenge to our ingenuity. As humanity gazes at its rusty deserts and shimmering ice caps, we see a reflection of ourselves, a species driven to explore, to understand, and to dream. Mars is a destination, a question, and a promise. A world that calls us to venture beyond our home and into the vast unknown. Mars, a distant and enigmatic world, shares its origins with the rest of the solar system, emerging from the swirling chaos of gas and dust that surrounded our young sun over 4.5 billion years ago. It began as a cluster of rocky fragments, bound together by gravity and fused by the immense heat of countless collisions. From these violent beginnings, Mars took shape as a terrestrial planet, its formation a testament to the forces that govern the universe. To understand Mars as it is today, we must first journey back to its birth, tracing the steps that shaped it into the planet we see now. A planet marked by extremes, contrasts, and the enduring evidence of a once dynamic world. Mars's story begins in the protoplanetary disk, a vast, rotating cloud of dust and gas left behind after the formation of the sun. Within this disk, gravity worked tirelessly, pulling together particles to form the building blocks of planets. Mars found its home in a region of the solar system that was rich in silicate materials, but lacked the density of gas and ice found farther from the sun. This positioning influenced its size, composition, and eventual destiny as a smaller, rocky planet with limited resources to build a thick atmosphere or retain substantial amounts of water. As Mars grew, it underwent a period of intense bombardment, a stage known as accretion. Countless impacts from asteroids and comets added mass and energy to the young planet, heating it to the point where its surface became a molten sea. During this time, Mars differentiated, meaning its heavier elements such as iron and nickel sank toward the center, forming a core, while lighter silicates rose to create a primitive crust and mantle. This process was not unique to Mars. It was shared by Earth, Venus, and Mercury. However, Mars's smaller size meant that it cooled more quickly, setting it on a path of geological dormancy far earlier than its larger neighbors. The first billion years of Mars's history, known as the Noachian epoch, were a time of dramatic change. Volcanic activity was rampant, as heat from the core escaped through the planet's crust, forming massive volcanoes like Olympus Mons. Lava flowed across the surface, reshaping the landscape and creating the vast plains we see today. During this period, Mars also experienced a heavy bombardment of asteroids and comets, leaving behind craters that still pockmark the southern highlands. These impacts not only shaped the surface but also delivered critical elements like water, potentially seeding the planet with the ingredients for life. Mars's volcanic activity during the Noachian epoch was unmatched, even by Earth. Olympus Mons, the tallest volcano in the solar system, began forming during this time. Its immense size, made possible by Mars's lower gravity and the absence of tectonic plate movement. Unlike Earth, where tectonic plates shift and create chains of smaller volcanoes, Mars's crust remained stationary, allowing magma to erupt repeatedly in the same location. This stationary crust also contributed to the formation of the Tharsis region, a vast volcanic plateau that dominates the western hemisphere of Mars. The weight of this region may have caused the crust to crack, creating the massive canyon system of Valles Marineris. But Mars's most intriguing feature from this early period is the evidence of water. Channels carved into the surface suggest that liquid water once flowed freely, forming rivers, lakes, and perhaps even oceans. These channels, visible from orbit, wind through the ancient terrain, hinting at a time when Mars had a thicker atmosphere capable of supporting a hydrological cycle. Mineral deposits, such as clays and sulfates, further support the idea that Mars was once a wetter, warmer world. These minerals form in the presence of water and have been found in abundance by rovers and orbiters, offering tantalizing clues about the planet's past climate. As Mars transitioned into the Hesperian epoch, roughly 3.7 billion years ago, the planet began to cool. Volcanic activity slowed, and the atmosphere started to thin, likely due to the loss of its magnetic field. Without this protective barrier, solar wind and radiation stripped away the atmosphere, reducing it to a thin layer of carbon dioxide. As the atmosphere disappeared, so did Mars's ability to retain heat, causing surface temperatures to drop. Water, once abundant, either froze beneath the surface or was lost to space, leaving behind the dry, dusty world we see today. The disappearance of Mars's magnetic field remains one of the most profound turning points in its history. On Earth, the magnetic field is generated by the movement of molten iron in the planet's core, creating a protective shield that deflects solar wind. Mars, however, is smaller and cooled more quickly, leading to the solidification of its core and the cessation of its dynamo. This loss left Mars vulnerable to the sun's relentless radiation, which stripped away the atmosphere and transformed its climate. Today, traces of the ancient magnetic field can still be detected in the planet's crust, particularly in the southern highlands, where magnetized rocks provide a faint echo of a time when Mars was shielded from the harshness of space. The final chapter in Mars's evolution, the Amazonian epoch, began about 3 billion years ago and continues to this day. This era is characterized by relative geological inactivity, with only sporadic volcanic eruptions and occasional impacts from asteroids and comets. The surface of Mars, shaped by billions of years of wind and dust, has become a desert frozen in time. Yet, even in its stillness, Mars remains dynamic in subtle ways. Seasonal changes in the polar ice caps, periodic dust storms, and faint traces of methane in the atmosphere suggest that the planet is not entirely lifeless, at least in terms of geological processes. Mars's journey from a molten, water-rich world to a barren desert is a story of transformation. It is a planet that once held the potential for life, with conditions that may have mirrored those of early Earth. Understanding how and why Mars changed offers valuable lessons not only about planetary evolution, but also about the factors that sustain life. It raises questions about our own planet's future and challenges us to think about the delicate balance that makes Earth habitable. Mars is a testament to the forces of creation and destruction that shape all planets. Its surface, scarred by impacts and sculpted by ancient rivers, tells a story of resilience in the face of cosmic upheaval. It is a world of contrasts, both dynamic and dormant, familiar and alien. As we study its past, we uncover not only the history of a distant planet, but also a piece of our own story, written in the stars billions of years ago. Mars has always been more than just a celestial object in the night sky. It is a symbol of mystery and potential, a world that has captured the imaginations of scientists, philosophers, and dreamers for centuries. But today, as we stand on the cusp of humanity's next great age of exploration, Mars represents something even greater. It is a frontier that challenges our understanding of life, a proving ground for our technologic ingenuity, and perhaps one day, a new home for humanity. The reasons to explore Mars are as varied as the planet itself, ranging from scientific discovery to existential necessity. Each reason underscores the importance of this small, rust-colored world as a key to humanity's future. One of the most compelling reasons to explore Mars lies in its potential to answer one of the most profound questions in science. Are we alone in the universe? Mars is unique in the solar system because it holds the most evidence of once having conditions suitable for life. Billions of years ago, Mars had a thicker atmosphere, flowing rivers, at least in microbial forms. Today, the surface of Mars is harsh and inhospitable, but traces of its wetter past remain etched into its landscape, in dried-up riverbeds and mineral deposits formed by water. Exploring these ancient environments could reveal whether life ever took hold on Mars, and if so, how it compares to life on Earth. The discovery of even the simplest microorganisms on Mars would be transformative. It would mean that life is not unique to Earth and could exist elsewhere in the cosmos. Such a discovery would deepen our understanding of biology, evolution, and the origins of life itself. It would also raise tantalizing new questions. If life began on Mars, did it arise independently, or did it share with friends on neutral Earth, perhaps carried between the planets on meteorites? These questions drive missions like the Perseverance rover, which is currently searching for biosignatures, chemical or physical evidence of past life, in Mars's ancient lake beds. Each discovery brings us one step closer to answering whether Mars was ever alive. Beyond the search for life, Mars offers a natural laboratory for studying planetary evolution. Unlike Earth, which is constantly reshaped by tectonic activity, weathering, and the movement of water, Mars has remained geologically static for billions of years. Its surface preserves a record of the solar system's history, from the intense bombardment of the early epochs to the gradual cooling of a planet's core. Studying Mars helps us understand how planets change over time, and why some, like Earth, remain habitable, while others, like Mars, become barren. This knowledge is crucial for understanding our own planet's past and future, and for identifying other potentially habitable worlds beyond our solar system. Mars is also a treasure trove of resources, making it a practical destination for exploration. Its surface contains materials that could be used to support human missions, from the water locked in its polar ice caps to the carbon dioxide in its atmosphere, which can be converted into oxygen and fuel. Learning to utilize these resources is not only critical for future Mars colonization, but also serves as a proving ground for technologies that could enable exploration of more distant worlds. The ability to live off the land, what scientists call in situ resource utilization, will determine the feasibility of establishing a sustainable human presence on Mars and beyond. The technological challenges of exploring Mars are immense, but they are also an opportunity to innovate. Landing a spacecraft on Mars is an achievement in itself, given the thin atmosphere and the need for precise control. Every mission to Mars has driven advancements in robotics, propulsion, materials science, and artificial intelligence. The development of rovers like Perseverance, which can autonomously navigate the Martian terrain, represents a leap forward in machine learning and remote operations. These technologies have applications far beyond space exploration, improving life on Earth in areas like autonomous vehicles, medical devices, and communication networks. Exploring Mars is also an opportunity to inspire. Throughout history, great endeavors have unified humanity and expanded our horizons, from the first ocean voyages to the Apollo missions that landed humans on the Moon. Mars represents the next great challenge, one that pushes the boundaries of what we are capable of achieving. The images of Mars sent back by rovers, showing alien landscapes that feel eerily familiar, ignite a sense of wonder and curiosity. They remind us of the vastness of the universe and our ability to reach beyond our limitations. Each mission to Mars inspires the next generation of scientists, engineers, and explorers who will carry humanity's legacy forward. But perhaps the most profound reason to explore Mars is existential. Mars represents a lifeboat, a second chance for humanity. Earth is our cradle, but it is also fragile, vulnerable to natural disasters, climate change, and even cosmic events like asteroid impacts. Establishing a human presence on Mars is not just about exploration, it is about ensuring the survival of our species. A self-sustaining colony on Mars would reduce the risk of extinction, providing a backup for humanity in the event of a global catastrophe. This vision, championed by scientists and visionaries like Carl Sagan and Elon Musk, is not just science fiction. It is a necessary step in humanity's long-term survival. Mars also challenges us to think about the kind of future we want to create. As we planned for human missions and eventual colonization, we are faced with ethical and philosophical questions about our role in the universe. Should we terraform Mars, transforming it into a habitable world, or preserve it as a natural laboratory? How do we ensure that exploration is conducted responsibly, respecting both the planet's environment and the scientific value it holds? These questions force us to confront our values and priorities, shaping not only our approach to Mars, but also how we view our relationship with Earth. Finally, exploring Mars is about discovery. It is about pushing the boundaries of what is known and venturing into the unknown. Mars is a challenge that demands ingenuity, perseverance, and collaboration. It is a reminder that humanity is at its best when we reach for the stars, driven by curiosity and a sense of shared purpose. Mars is not just a destination, it is a journey, one that will change how we see the universe and our place within it. In the end, the reasons to explore Mars are as much about us as they are about the planet itself. Mars challenges us to imagine a future where humanity is no longer confined to one world. It invites us to ask the big questions about life, survival, and what it means to be human. As we take our first steps on this journey, Mars becomes more than a distant planet. It becomes a mirror, reflecting our hopes, fears, and aspirations. It is a place where science and imagination converge, offering a glimpse of what lies beyond the horizon, and what we are capable of achieving when we dare to dream. Mars, a world frozen in time, holds the story of a planet that once teemed with geological and atmospheric activity. Its surface, with its craters, canyons, and ancient riverbeds, is a record of billions of years of planetary evolution. Unlike Earth, where tectonic forces and erosion constantly reshape the landscape, Mars has preserved much of its past in its stark and rugged terrain. To understand Mars today, we must unravel its geological and atmospheric history, a tale of creation, transformation, and eventual dormancy that has left us with the barren desert we see now. Mars began its journey more than 4.5 billion years ago, forming in the protoplanetary disk of dust and gas that surrounded the young sun. In those early days, Mars was a molten sphere, shaped by the intense heat of collisions and the radioactive decay of its core. As it cooled, Mars differentiated, forming a dense core of iron and nickel, a silicate mantle, and a primitive crust. This process set the stage for the planet's geological evolution, creating the layers that still define its structure today. During the Noachian epoch, countless asteroids in the southern highlands, leaving behind a pockmarked surface to form vast plains and massive shield volcanoes. At the same time, Mars was bombarded by countless asteroids and comets, leaving behind a pockmarked surface in the southern highlands. These impacts not only shaped the terrain, but also delivered water and organic compounds to the planet, potentially creating the conditions necessary for life. The evidence of this tumultuous period is written across Mars's surface. The southern hemisphere, dominated by craters and rugged terrain, is one of the oldest landscapes in the solar system. These craters, some spanning hundreds of kilometers, are a window into the past, revealing the intensity of the early solar system's bombardment. In contrast, the northern hemisphere is smoother and younger, likely the result of volcanic resurfacing, or a catastrophic event that reshaped the region. But what truly sets the Noachian epoch apart is the presence of liquid water. During this time, Mars had a thicker atmosphere, capable of trapping heat and allowing water to flow across the surface. Channels carved by ancient rivers wind through the landscape, their sinuous paths a testament to the planet's wetter past. In some areas, deltas and lake beds remain, their sediments holding clues about the chemistry of the water and the possibility of life. Rovers like Curiosity and Perseverance have explored these ancient environments, uncovering minerals like clays and sulfates that form in the presence of water. These discoveries suggest that Mars was not only warm and wet, but also potentially habitable. As Mars transitioned into the Hesperian epoch, roughly 3.7 billion years ago, the planet began to change. Volcanic activity continued, though less intensely, creating features like the Tharsis Volcanic Plateau. This immense region, home to Olympus Mons and several other giant volcanoes, may have influenced the planet's climate by releasing vast amounts of gases into the atmosphere. At the same time, Mars's magnetic field began to wane. Without this protective shield, solar wind and radiation stripped away the atmosphere, reducing it to a thin layer of carbon dioxide. This loss marked the beginning of a dramatic cooling period. As Mars's ability to retain heat diminished, the water that once flowed freely across the surface either froze beneath the ground or was lost to space, leaving behind the dry riverbeds and salt deposits we see today. The Amazonian epoch, which began around 3 billion years ago and continues to this day, represents the final chapter in Mars's geological history. During this time, volcanic activity became sporadic, and the planet's surface was shaped more by wind and dust than by tectonic or hydrological processes. The iconic dust storms that sweep across Mars are a defining feature of this era, eroding rocks and sculpting the landscape into new forms. Though the planet appears dormant, subtle changes in the polar ice caps and faint traces of methane in the atmosphere suggest that Mars is not entirely static. One of the most fascinating aspects of Mars's geological history is its volcanoes. Olympus Mons, the tallest volcano in the solar system, stands as a monument to the planet's volcanic past. Its gentle slopes and immense size are the result of repeated eruptions over millions of years, made possible by Mars's stationary crust. Unlike Earth, where tectonic plates shift and create chains of smaller volcanoes, Mars's crust allowed magma to build in the same location for thousands of years. The Tharsis region, home to Olympus Mons and several other giant volcanoes, is a testament to the power of Mars's volcanic activity and its influence on the planet's evolution. Equally impressive is the canyon system of Valles Marineris, a scar across the surface that stretches over 4,000 kilometers. This colossal feature, formed by tectonic forces and erosion, reveals the planet's dynamic past. Its walls expose layers of rock that hold clues about Mars's history, including the presence of water and volcanic activity. Exploring these layers is like reading the pages of a geological book, each chapter revealing a new aspect of the planet's story. While Mars's atmosphere has played a central role in its evolution, in its early history, a thick atmosphere of carbon dioxide, water vapor, and other gases created a greenhouse effect that kept the planet warm enough for liquid water to exist. Over time, as the magnetic field disappeared, the atmosphere thinned and the greenhouse effect diminished. Today, Mars's atmosphere is a tenuous shell composed mostly of carbon dioxide with trace amounts of nitrogen, argon, and water vapor. Its thinness means that temperatures swing dramatically between day and night, and a lack of oxygen makes it unbreathable for humans. Despite its thin atmosphere, Mars's climate is not entirely lifeless. Seasonal changes in the polar ice caps, driven by the planet's axial tilt, create dynamic patterns of freezing and sublimation. During winter, carbon dioxide from the atmosphere freezes at the poles, forming a layer of dry ice. In the spring and summer, this ice sublimates back into gas, driving winds and creating seasonal flows of gas and dust. These processes, though subtle, hint at the complexity of Mars's climate and its potential to change over time. Understanding Mars's geological and atmospheric history is not just about studying another planet. It is about learning more about the processes that shape all terrestrial worlds, including Earth. Mars offers a glimpse into a past that we cannot see on our own planet, where tectonic activity and erosion have erased much of the early record. By studying Mars, we can better understand the factors that make planets habitable, the conditions that lead to the loss of atmospheres, and the delicate balance required to sustain life. Mars' history is one of transformation, from a warm, water-rich world to the cold, arid desert we see today. It is a story of extremes, preserved in the rocks, ice, and dust that cover its surface. As we continue to explore Mars, we are uncovering not only the history of a distant planet, but also the shared history of our solar system, a history that binds Earth and Mars together as neighbors in space and time. Mars today is a cold, arid world, its surface a wind-swept desert where temperatures often plunge to uninhabitable extremes. Yet the story of Mars is not one of unchanging desolation. Beneath its dusty red exterior lies evidence of a planet that was once very different. Wet and perhaps even vast oceans spanned its surface. Mars was once warmer and wetter, conditions that may have supported life. The search for traces of this ancient world has been at the heart of our exploration of the Red Planet, and the discoveries made so far paint a picture of a planet transformed by time. One of the most striking pieces of evidence for a wetter Mars comes from the channels and valleys that scar its surface. From orbit, these features resemble dried-up riverbeds, their winding paths cutting through ancient terrain. These channels, some stretching for hundreds of kilometers, are unmistakable signs that liquid water once flowed across the surface. The branching patterns of certain valleys suggest that they were formed by long-lasting rivers, while others appear to have been carved rapidly, possibly by catastrophic floods unleashed by melting ice or volcanic activity. These observations indicate that water was not only present on Mars, but played a significant role in shaping its landscape. Beyond the channels, Mars holds the remnants of ancient lakes and deltas, places where water pooled and sediments settled over time. The Jezero crater, a 45-kilometer-wide impact basin currently being explored by NASA's Perseverance rover, is one such site. Satellite images of Jezero revealed a fan-shaped delta where a river once emptied into a lake, depositing layers of clay and other minerals that form in the presence of water. These sediments are a time capsule, preserving the chemical and geological record of the lake's existence. By studying these layers, scientists hope to uncover clues about Mars's climate and its potential for harboring life. The story of water on Mars extends beyond surface features. Minerals found across the planet provide chemical evidence of a wetter past. Clays, sulfates, and carbonates, minerals that form in liquid water, have been detected by orbiters and rovers alike. The Curiosity rover, which has been exploring Gale craters since 2012, discovered layers of sedimentary rock that were likely deposited in a long-gone lake. These rocks contain clays formed in neutral pH water, conditions considered favorable for life. In other regions, sulfates found in Martian soil suggest the presence of salty, acidic water, while carbonates point to ancient interactions between water and carbon dioxide from the atmosphere. These discoveries not only confirm the presence of water but also hint at the complexity of Mars's aquatic environments. The possibility of ancient oceans on Mars is one of the most intriguing questions in planetary science. Some researchers believe that Mars's northern hemisphere, a low-lying region known as the Northern Plains, may have once been home to a vast ocean. Topographic maps created from orbital data reveal a boundary that resembles an ancient shoreline, encircling the region like a faint echo of a long-lost sea. Supporting this theory are sedimentary deposits and channels that appear to have drained into the basin, suggesting that water once pooled there on a massive scale. If this ocean existed, it would have been a vital part of Mars's climate system, influencing weather patterns and the movement of water across the planet. Yet, the question of how long water persisted on Mars remains unresolved. Did the planet have a stable, warm climate for millions of years, or were these wet periods brief and episodic? Some scientists argue that Mars's atmosphere was too thin to sustain long-term liquid water, suggesting that its rivers and lakes may have been the result of short-term warming events caused by volcanic eruptions, asteroid impacts, or shifts in the planet's orbit. Others propose that Mars's thicker atmosphere in the distant past allowed for a sustained hydrological cycle, with rain and snow feeding rivers and lakes. The loss of Mars's water is a story of planetary transformation. Over billions of years, the planet's atmosphere thinned, and its ability to retain liquid water diminished. Without a magnetic field to shield it, Mars was exposed to the relentless solar wind, which stripped away much of its atmosphere. As the air pressure dropped and temperatures fell, water on the surface either froze or sublimated directly into the atmosphere. Today, most of Mars's water is locked away in its polar ice caps and subsurface layers, preserved as frozen reservoirs beneath the soil. Despite this, Mars still shows occasional hints of modern water activity. Dark streaks, known as recurring slope linii, appear on certain slopes during warmer seasons, suggesting the presence of liquid brines, salty water that can remain liquid at lower temperatures. These streaks fade during colder months, creating a tantalizing mystery about their origin. While they may not represent flowing water in the traditional sense, they hint at the possibility of liquid activity just beneath the surface. The implications of Mars's wetter past extend far beyond geology. Where there is water, there is the potential for life. On Earth, water is a fundamental requirement for every known living organism, and its presence on Mars raises the question of whether life once existed there. Even if Mars's ancient waters did not support life, they provide a blueprint for understanding the conditions necessary for life to arise. By studying these environments, scientists can refine their search for habitable worlds beyond our solar system, identifying planets with similar histories and climates. Mars's watery past also informs our plans for future exploration. Water is a critical resource for human missions, providing drinking water, oxygen, and fuel. Knowing where water exists on Mars and how accessible it is will be essential for establishing a sustainable human presence. The prospect of mining ice from the polar regions or extracting water from hydrated minerals could transform the feasibility of colonizing Mars, turning the planet into a stepping stone for humanity's expansion into the solar system. The evidence of Mars's warmer, wetter past is a reminder of how dramatically planets can change over time. Once, Mars may have been a vibrant world, its surface shaped by rivers and lakes, its atmosphere thick enough to sustain a water cycle. Today, it is a cold and desolate place, its rivers long dry and its lakes turned to dust. This transformation holds lessons for Earth, showing how shifts in climate and atmospheric conditions can reshape a planet's destiny. By studying Mars, we gain not only a deeper understanding of its history, but also a greater appreciation for the delicate balance that makes Earth habitable. Mars's past is a story of potential, a glimpse of what might have been. Its ancient waters, now gone, whisper of a world that could have supported life, a world that once resembled Earth in ways we are only beginning to understand. As we continue to explore the Red Planet, we are uncovering pieces of its history, assembling a picture of a planet that has been shaped by water, wind, and time. Mars's past may be written in its rocks and soil, but its lessons resonate far beyond, offering insights into the history of our solar system and the future of exploration. Mars, with its rocky plains and faint pinkish skies, might seem like a distant cousin to Earth, a place that could one day become a second home for humanity. But behind its familiar appearance lies a world of stark contrasts and formidable dangers. The challenges of Mars are not just technical, they are existential, posing questions about survival, adaptation, and the limits of human ingenuity. Before we can consider Mars as a destination for humans, we must confront the extreme environmental conditions that make it one of the most inhospitable places in the solar system. The thin atmosphere of Mars is one of its most defining and challenging features. Composed primarily of carbon dioxide, it accounts for less than 1% of the atmospheric pressure found at sea level on Earth. For humans, this means there is no breathable air, and the lack of pressure would cause bodily fluids to boil at relatively low temperatures, making survival impossible without pressurized suits or habitats. This thin atmosphere also provides little insulation, leading to dramatic temperature swings. During the day, temperatures might rise to a relatively mild 20 degrees Celsius near the equator, only to plummet to minus 100 degrees Celsius or lower at night. These extremes create a harsh environment where technology and infrastructure must be designed to withstand constant thermal stress. Mars's lack of a protective magnetic field compounds these challenges. On Earth, our magnetic field deflects much of the harmful radiation from the sun and cosmic rays from beyond our solar system. Mars, however, has no such shield. Its magnetic field disappeared billions of years ago, leaving the planet exposed to radiation levels that are far higher than what we experience on Earth. This radiation is not only a danger to human health, increasing the risk of cancer and other illnesses, but also a threat to electronic systems, which must be hardened against constant exposure to high-energy particles. The surface of Mars, while captivating, is another obstacle. Covered in fine, powdery dust, the regolith of Mars is not like the soil we know on Earth. This dust, rich in perchlorates, salts that are toxic to humans, can infiltrate equipment, clog machinery, and pose respiratory risks to astronauts. Its electrostatic properties make it cling to surfaces, including spacesuits, creating potential contamination issues for both humans and habitats. The jagged particles of Martian dust are abrasive, wearing down seals and joints over time, and its pervasive presence means that managing dust will be a critical aspect of any long-term mission. Radiation and dust are not the only hazards. Mars's low gravity, which is about 38% of Earth's, presents unique challenges for human physiology. While the reduced gravity would make tasks like lifting and moving heavy objects easier, prolonged exposure to such conditions could have serious effects on the human body. Studies conducted aboard the International Space Station have shown that microgravity environments lead to muscle atrophy, bone density loss, and changes in the cardiovascular system. Although Mars's gravity is higher than the microgravity of space, it is still far from Earth's, and the long-term impacts on human health remain uncertain. Countermeasures, such as rigorous exercise regimens and possible medical interventions, would be necessary to maintain physical health during extended stays on Mars. Water, a necessity for life, is another challenge on Mars. While evidence suggests that significant amounts of water exist as ice, especially in the polar regions, accessing and utilizing this resource is no small task. The water locked in subsurface layers or bound in hydrated minerals must be extracted and purified before it can be used for drinking, agriculture, or fuel production. This requires advanced technologies and significant energy, resources that will be at a premium on Mars. Without reliable access to water, long-term missions or colonies would be impossible, underscoring the importance of identifying and mapping water reserves as part of any exploration effort. Even the very act of reaching Mars is fraught with difficulty. The journey from Earth to Mars takes approximately 6 to 9 months, depending on the alignment of the planets. During this time, astronauts are exposed to the dangers of space travel, including microgravity, isolation, and radiation. Spacecraft must be designed to protect their occupants from solar flares and cosmic rays, while also providing systems for life support, waste management, and psychological well-being. The journey itself is just the beginning. Landing on Mars presents its own set of challenges. Mars's atmosphere, while thin, is thick enough to pose a problem for entry, descent, and landing. Spacecraft traveling to Mars must slow down from speeds of over 200 kilometers per hour, navigating a delicate balance between heat, friction, and parachute deployment. The infamous 7 minutes of terror refers to the harrowing descent phase, during which a spacecraft must autonomously execute a series of maneuvers to land safely. The success of missions like Perseverance and Curiosity demonstrates our ability to overcome these challenges, but landing larger payloads, such as habitats or crewed vehicles, will require even more advanced technology. Once on Mars, the isolation and psychological toll of living on an alien planet become significant hurdles. Unlike the Moon, which is only a few days away, Mars is so distant that communication with Earth is delayed by up to 22 minutes round trip. This delay makes real-time conversations impossible and forces astronauts to operate with a high degree of autonomy. The psychological effects of such isolation, combined with the confined living conditions and the ever-present dangers of the Martian environment, could strain even the most resilient individuals. Addressing these challenges requires careful mission planning, robust mental health support, and the selection of crews with exceptional teamwork and problem-solving skills. Mars's extreme conditions also demand energy systems that are both reliable and sustainable. Solar power, while viable in certain regions, is limited by the planet's frequent dust storms, which can obscure sunlight for weeks at a time. Nuclear energy, often proposed as an alternative, offers a more consistent power source, but brings challenges in terms of transportation, safety, and public perception. The development of energy infrastructure on Mars will be a critical factor in the success of any mission, determining the feasibility of running habitats, life support systems, and scientific equipment. Despite these formidable challenges, Mars represents an opportunity to push the boundaries of human capability. Each obstacle, whether it is the lack of air, the intense radiation, or the logistical complexities of reaching and surviving on Mars, forces us to innovate, to create technologies and strategies that not only make Mars exploration possible, but also benefit life on Earth. Solutions developed for Mars, from advanced water purification systems to autonomous robots, have the potential to address global challenges, improving sustainability, resilience, and quality of life on our home planet. Mars is not just a destination, it is a crucible of human ingenuity and determination. The challenges of Mars are a reminder that exploration has always been fraught with risk, from the first ocean crossings to the moon landings. Yet it is precisely these challenges that make Mars worth pursuing. By overcoming them, we prove not only that we can survive on another planet, but also that we can thrive in the face of adversity. Mars tests our limits and inspires our greatest achievements, offering the chance to write a new chapter in the story of humanity. Mars, the enigmatic red planet, has captivated scientists and explorers with its tantalizing hints of a wetter past and the possibility of life. While its surface today is dry and barren, strewn with dust and rocky debris, evidence suggests that Mars was once a world where water flowed freely, a vital ingredient for life as we understand it. The search for water and life on Mars is not just a quest to understand another planet. It is a journey to answer profound questions about the origins of life and our place in the universe. Water is the cornerstone of this search, as life as we know it cannot exist without it. For decades, scientists have scrutinized Mars for signs of past or present water, and their findings have revolutionized our understanding of the planet. From orbiters mapping its surface to rovers analyzing its soil and rocks, every mission has brought new insights into Mars's hydrological history. The evidence for water is overwhelming. Ancient river valleys, dry lake beds, and the mineral fingerprints of water's chemical interactions are etched into the Martian landscape. One of the most compelling pieces of evidence for past water on Mars is the network of valleys and channels that wind across its surface. These features, visible from orbit, resemble the dried-up riverbeds and floodplains found on Earth. They suggest that Mars once had a thicker atmosphere, warm enough to allow liquid water to exist on the surface. In some regions, the channels branch and converge in patterns unmistakably shaped by flowing water, hinting at a planet that was once alive with rivers and streams. Rovers like Curiosity and Perseverance have explored areas believed to have hosted ancient lakes and deltas. These missions have uncovered layers of sedimentary rock that could only have formed in standing water. In Gale Crater, where Curiosity continues its mission, scientists have found evidence of a long-gone lake that persisted for millions of years. The rocks in this crater contain clays and sulfates, minerals that form in water and can preserve biosignatures, chemical or structural markers of life. Similarly, Perseverance is now investigating Jezero Crater, a site with a well-preserved delta that once emptied into a vast lake. This delta's sediments may hold clues to Mars's past environment and any life that might have thrived there. The search for water extends beyond visible surface features. Subsurface exploration has revealed vast reservoirs of frozen water locked beneath Mars's surface and within its polar ice caps. Radar instruments aboard orbiters, such as the European Space Agency's Mars Express and NASA's Mars Reconnaissance Orbiter, have detected layers of ice buried beneath dust and rock. These discoveries are not only crucial for understanding Mars's climate history, but also hold practical implications for future exploration. Subsurface water could serve as a resource for human missions, providing drinking water, oxygen, and fuel. In recent years, scientists have also detected seasonal changes in the Martian atmosphere that suggest the possibility of liquid water activity even today. Dark streaks, called recurring slope lineae, RSL, appear on certain slopes during warmer months and fade as temperatures drop. These streaks may be caused by briny water, highly salient liquid that remains unfrozen at low temperatures, seeping from the ground. While the exact mechanism behind these features is still debated, their existence hints at the potential for active hydrological processes on Mars. Where there is water, the possibility of life follows. The question of whether life ever existed, or might still exist, on Mars is one of the most profound inquiries in planetary science. On Earth, water provides the foundation for life in even the most extreme environments, from boiling hot springs to the frigid depths of Antarctica. If Mars had liquid water in its past, it could have supported microbial life, and remnants of that life might still be preserved in the planet's rocks and soil. The discovery of organic molecules on Mars has added to the intrigue. Curiosity's instruments have detected these carbon-based compounds in the Martian soil, raising the possibility that the building blocks of life were present on the planet. While these molecules could also have non-biological origins, their presence is an encouraging sign for astrobiologists. Organic molecules are essential for life, and their persistence on Mars suggests that the planet had the chemical ingredients necessary for biology to emerge. Perseverance's mission is designed to take the search for life one step further. It is collecting rock and soil samples from Jezero Crater, where conditions for ancient life were likely favorable. These samples will eventually be returned to Earth in a future mission, allowing scientists to analyze them with tools far more advanced than those available on the rover itself. By examining these samples for biosignatures, researchers hope to find definitive evidence of whether life ever existed on Mars. The search for life is not confined to Mars's past. Some scientists believe that life could still exist on the planet, hiding in the subsurface where conditions are more stable and protected from radiation. On Earth, microbial life thrives in environments previously thought to be uninhabitable, such as deep underground or within Antarctic ice. Mars's subsurface, with its potential reserves of liquid water and protection from the harsh surface environment, could offer a similar refuge for extremophiles, organisms adapted to extreme conditions. The possibility of life on Mars raises profound philosophical questions. If life arose independently on Mars, it would suggest that life is not unique to Earth, but a common occurrence in the universe, wherever conditions allow. This would have staggering implications for our understanding of biology and the potential for life on exoplanets orbiting distant stars. On the other hand, if life on Mars and Earth share a common origin, perhaps through meteorites transferring material between the two planets, it would mean that our solar system is interconnected in ways we are only beginning to comprehend. Beyond the scientific implications, the search for water and life on Mars has practical importance for humanity's future. Water is a critical resource for human missions, not only for sustaining life, but also for producing oxygen and fuel. Identifying accessible water reserves on Mars will be key to establishing a sustainable human presence. Furthermore, understanding the conditions that allowed water to exist on Mars and the processes that led to its loss can provide valuable lessons for protecting Earth's own environment. The search for water and life on Mars is a journey that touches on some of the most fundamental questions we can ask. How did life begin? Are we alone? What does it take to sustain life on a planet? Each discovery on Mars brings us closer to answering these questions, but it also reveals the complexity and wonder of the universe. Mars, with its ancient rivers and hidden ice, is more than a planet. It is a bridge between science and philosophy, a reminder that the search for life is, at its core, a search for ourselves. The idea of humans walking on Mars has captivated the imagination of explorers, scientists, and storytellers for generations. From the pages of science fiction to detailed engineering plans, the dream of reaching the Red Planet has evolved into a tangible goal. Human missions to Mars represent the next great leap in space exploration, a challenge that combines cutting-edge technology, profound scientific inquiry, and a deep-seated drive to push the boundaries of human potential. But what would it take to turn this dream into reality, and what would it mean for humanity? The journey to Mars begins with a simple yet monumental challenge, crossing the vast gulf of space that separates our two worlds. Mars and Earth align favorably for interplanetary travel approximately every 26 months, when the planets are at their closest. Even then, the trip to Mars takes 6 to 9 months, depending on the trajectory and speed of the spacecraft. During this journey, astronauts would be confined to a spacecraft for an extended period, facing the dual challenges of isolation and exposure to cosmic radiation. Designing a spacecraft capable of protecting its crew while providing a livable environment for such a long journey is one of the most significant hurdles in planning a mission to Mars. Radiation is one of the primary dangers for astronauts traveling to Mars. Unlike Earth, which is shielded by a robust magnetic field and atmosphere, Space offers no such protection. Astronauts on a Mars mission would be exposed to cosmic rays and solar radiation, increasing their risk of cancer, radiation sickness, and other health issues. Engineers are exploring solutions such as advanced shielding materials, radiation shelters, and even water-filled walls that could absorb harmful particles. Despite these efforts, the risk remains a sobering reality of interplanetary travel. The psychological challenges of a Mars mission are equally daunting. A crew bound for Mars would spend months in a confined space, far from family, friends, and the comforts of Earth. Communication delays, up to 22 minutes round trip, would make real-time conversations with Earth impossible, forcing astronauts to operate autonomously. Maintaining mental health and team cohesion under such conditions is a critical focus for mission planners. Strategies include rigorous psychological screening during crew selection, virtual reality tools to simulate Earth-like environments, and robust support systems to address the mental health needs of the crew. When the spacecraft finally arrives at Mars, another monumental challenge awaits: landing. Mars's thin atmosphere poses a unique problem. It is too dense to ignore, but too thin to rely on for effective aerodynamic braking. Spacecraft must navigate this tricky environment, slowing from speeds of over 200 kilometers per hour to a gentle touchdown. Past missions, such as the Curiosity and Perseverance rovers, have used innovative techniques like heat shields, parachutes, and the sky crane system to achieve successful landings. However, landing humans and their equipment significantly heavier payloads than robotic rovers will require even more advanced systems, potentially involving inflatable heat shields, retropropulsion, and precision navigation technologies. Once on the surface, the challenges of living and working on Mars come into sharp focus. The environment is unforgiving, with average temperatures hovering around 60 degrees Celsius and frequent dust storms that can last for weeks. Mars's thin atmosphere, composed mostly of carbon dioxide, provides no protection from harmful solar radiation or micrometeoroid. Any human presence on Mars will rely on habitats designed to maintain Earth-like conditions, including breathable air, regulated temperature, and protection from radiation. These habitats must be not only functional but also sustainable. Supplying everything from Earth is neither practical nor cost-effective, so future missions will depend on utilizing local resources, a concept known as in-situ resource utilization, ISRU. One of the most promising applications of ISRU is extracting oxygen from Mars's carbon dioxide-rich atmosphere. NASA's Perseverance rover is already testing this technology with its MOXIE instrument, which successfully produces small amounts of oxygen. Scaling up such processes will be critical for supporting human crews and producing fuel for return trips to Earth. Water is another essential resource for human missions. While evidence of frozen water has been found on Mars, accessing it will require drilling and processing technologies that are still in development. Water is not only vital for drinking and hygiene, but also serves as a raw material for generating oxygen and hydrogen, the latter of which can be used as rocket fuel. Identifying reliable sources of water on Mars will be a key milestone in making human missions sustainable. Food production presents another significant hurdle. Transporting enough food for a multi-year mission is impractical, so astronauts will need to grow their own food. Experiments aboard the International Space Station have demonstrated that plants can grow in microgravity, but Mars introduces new challenges, such as its lower gravity and lack of natural soil. Scientists are exploring hydroponic and aeroponic farming techniques, as well as ways to use Martian regolith as a growing medium. The success of these efforts will determine how self-sufficient future Mars colonies can become. The long-term effects of Mars's low gravity, about 38% of Earth's, on the human body are still unknown. On Earth, our muscles and bones are constantly working against gravity, maintaining their strength and density. In the reduced gravity of Mars, astronauts may experience muscle atrophy, bone loss, and changes to their cardiovascular systems. Addressing these issues will require rigorous exercise regimens and potentially medical interventions. Understanding how the human body adapts to Mars is a critical area of research, with implications for even longer missions, such as those to the outer planets or beyond our solar system. Despite these challenges, the rewards of human missions to Mars are profound. Scientifically, human explorers can achieve far more than robotic missions. While rovers like Perseverance are equipped with advanced instruments, they are limited by their programming and the delay in communication with Earth. Astronauts, by contrast, can make real-time decisions, adapt to unexpected situations, and conduct experiments with a level of precision and creativity that robots cannot match. The ability to explore Martian caves, examine rock formations in detail, and search for signs of life firsthand would mark a new era of planetary science. Human missions to Mars are not just about science. They are about pushing the boundaries of what humanity can achieve. The challenges of Mars test our ingenuity, resilience, and ability to work together as a global community. Nations and private organizations around the world are contributing to this effort, from NASA's Artemis program to SpaceX's ambitious Starship plans. Each step toward Mars, whether it is developing new propulsion systems or testing habitats in extreme environments on Earth, brings us closer to realizing the dream of becoming a multi-planetary species. Mars represents the ultimate challenge, a destination that requires us to rethink what is possible and overcome obstacles that test the limits of our knowledge and capabilities. But it is precisely these challenges that make Mars worth pursuing. Reaching the red planet would be more than a technological triumph. It would be a defining moment in human history, a testament to our capacity for exploration and innovation. As we prepare for the first human footprints on Mars, we are not just planning a mission, we are embarking on a journey that will shape the future of humanity. The story of Mars is inseparable from the machines that have ventured there on humanity's behalf. From the earliest flybys to today's sophisticated rovers, robotic exploration has transformed our understanding of the red planet. These machines are our surrogates, equipped with the tools to investigate a world that is too distant and hostile for human explorers, at least for now. Each mission builds on the successes and lessons of its predecessors, pushing the boundaries of what we know and preparing the way for future human missions. Robotic exploration is not just a precursor to human presence. It is a testament to our ingenuity and desire to uncover the secrets of Mars. The journey began in the 1960s during the early days of the space age, when the United States and the Soviet Union competed to send the first spacecraft to Mars. These early attempts were fraught with challenges, as most missions failed to reach their target or transmit meaningful data. However, in 1965, NASA's Mariner 4 became the first spacecraft to successfully fly past Mars, capturing 21 grainy images of its surface. These images revealed a barren and cratered world, dashing early hopes that Mars might be teeming with life, but igniting new questions about its geology and history. In the decades that followed, robotic missions became more ambitious. The Viking program of the 1970s marked a significant milestone, with Viking 1 and Viking 2 becoming the first spacecraft to land on Mars and conduct detailed scientific experiments. Equipped with cameras, weather instruments, and life detection experiments, the Viking landers provided the first panoramic images of the Martian surface, showing a desolate yet captivating landscape. Although the life detection experiments yielded inconclusive results, Viking laid the groundwork for future exploration, proving that Mars could be studied in situ. The 1990s ushered in a new era of Mars exploration, driven by advances in technology and a renewed commitment to understanding the Red Planet. NASA's Mars Pathfinder mission, launched in 1996, was a watershed moment. It featured the Sojourner rover, a small six-wheeled robot that became the first rover to traverse the Martian surface. Sojourner demonstrated the feasibility of mobile exploration, capturing detailed images of rocks and soil while testing methods for future missions. Its success paved the way for a new generation of robotic explorers capable of venturing farther and doing more. The early 2000s saw the arrival of Spirit and Opportunity, twin rovers that revolutionized our understanding of Mars. These solar-powered robots landed on opposite sides of the planet in 2004, tasked with searching for evidence of past water. They far exceeded their expected lifespans, with Opportunity continuing to operate for nearly 15 years. During their missions, the rovers discovered minerals that form in liquid water, such as hematite and gypsum, providing some of the strongest evidence yet that Mars was once a wetter world. Their journeys across vast plains, up hills, and into craters captured the imagination of millions, turning the rovers into symbols of perseverance and exploration. The next leap in robotic exploration came with Curiosity, a nuclear-powered rover that landed in Gale Crater in 2012. Curiosity was designed to answer one of the most fundamental questions about Mars. Could it have supported life? Equipped with a suite of advanced instruments, including a laser spectrometer and a robotic arm capable of drilling into rocks, Curiosity has uncovered compelling evidence of ancient habitability. It has detected organic molecules, discovered clays that form in neutral pH water, and measured methane in the atmosphere, a potential indicator of biological activity. Curiosity's discoveries have provided a deeper understanding of Mars's past environment and set the stage for even more ambitious missions. In 2021, NASA's Perseverance rover arrived on Mars, bringing with it new capabilities and a bold mission to search for signs of ancient life and collect samples for future return to Earth. Perseverance landed in Jezero Crater, a site that once hosted a river delta and a lake. Its instruments are among the most advanced ever sent to Mars, capable of analyzing the chemical and mineral composition of rocks at microscopic scales. It is also equipped with MOXIE, a device that produces oxygen from the carbon dioxide in Mars's atmosphere, demonstrating a technology that could be critical for future human missions. Perhaps most importantly, Perseverance is collecting rock and soil samples that will eventually be returned to Earth, allowing scientists to study them with tools far more advanced than those on the rover. One of Perseverance's most groundbreaking achievements has been the deployment of Ingenuity, a small helicopter that made history as the first powered flight on another planet. Ingenuity's flights, initially intended as a technology demonstration, have proven invaluable for scouting terrain and assisting Perseverance in its exploration. The success of Ingenuity has opened new possibilities for aerial exploration on Mars, paving the way for future missions that could include fleets of drones to map, survey, and explore areas inaccessible to rovers. Orbiters have also played a crucial role in robotic exploration, providing a bird's-eye view of Mars and supporting surface missions. The Mars Reconnaissance Orbiter, MRO, for example, has been in orbit since 2006, capturing high-resolution images that have revealed details as small as a meter across. Its instruments have mapped water ice beneath the surface, studied weather patterns, and identified landing sites for future missions. Other orbiters, such as India's Mars Orbiter mission and the European Space Agency's Mars Express, have expanded our understanding of the planet's atmosphere, geology, and climate. Robotic exploration has not been limited to the search for water and life. It has also helped us prepare for future human missions. The InSight lander, which arrived on Mars in 2018, is studying the planet's interior, measuring seismic activity and heat flow to better understand its structure and history. These data are critical for designing habitats and other infrastructure that can withstand Mars's unique conditions. Similarly, the ExoMars program, a collaboration between the European Space Agency and Russia, aims to drill beneath the surface to search for signs of life and study the planet's subsurface environment. Every robotic mission to Mars has built upon the successes and challenges of those that came before it. Together, they form a mosaic of discovery, each piece adding to our understanding of a planet that is both familiar and alien. The insights gained from these missions have not only transformed our knowledge of Mars, but also inspired humanity to dream bigger, pushing the boundaries of what is possible in exploration and science. Robotic exploration is a testament to human ingenuity and perseverance. These machines, traveling millions of kilometers to a distant world, represent the best of what we can achieve when we combine curiosity with innovation. They are our eyes, ears, and hands on Mars, uncovering the secrets of a planet that has fascinated humanity for centuries. As we prepare for the next chapter in Mars exploration, these robots will continue to lead the way, blazing a trail for the first humans to follow. Mars, the bright red star that moves steadily across our night sky, has fueled human curiosity for millennia. Long before telescopes revealed its true nature, Mars was a canvas onto which civilizations projected their hopes, fears, and fantasies. From early myths to the scientific errors of the modern era, Mars has been both a source of inspiration and a victim of misunderstanding. These misconceptions, while often rooted in limited technology or cultural bias, are an essential part of the planet's story, reflecting humanity's evolving relationship with the cosmos. The first misconceptions about Mars emerged from ancient mythology. To the Babylonians, it was Nergal, the god of war and destruction, its reddish glow evoking blood and fire. The Greeks called it Ares, while the Romans named it Mars, their own war deity. This association with war persisted for centuries, coloring the way humans thought about the planet. Its apparent brightness and rapid movement across the sky added to its mystique, making it a celestial symbol of power and aggression. As astronomy advanced, Mars remained a focal point of speculation. By the 17th century, telescopes allowed astronomers to glimpse Mars's surface for the first time, revealing faint markings in polar ice caps that seemed to wax and wane with the seasons. These observations suggested that Mars might be a dynamic world, a place where climate and geography changed over time. Early astronomers, including Christian Huygens and Giovanni Cassini, speculated that Mars might be more Earth-like than previously thought, sparking dreams of finding life on its surface. The 19th century brought a new wave of interest in Mars, driven by better telescopes and the burgeoning field of planetary science. One of the most influential figures of this era was Giovanni Schiaparelli, an Italian astronomer who, in 1877, created detailed maps of Mars. Schiaparelli noted long, dark lines crisscrossing the planet, which he called canali, an Italian word meaning channels. In his writings, Schiaparelli suggested these features might be natural waterways, remnants of ancient rivers, or channels carved by liquid water. However, when Schiaparelli's work was translated into English, canali was misinterpreted as canals, implying artificial structures built by intelligent beings. This mistranslation ignited widespread speculation that Mars was home to an advanced civilization. American astronomer Percival Lowell became one of the most vocal proponents of this idea. Convinced that the canals were evidence of intelligent life, Lowell spent years mapping them in painstaking detail and writing books that captured the public's imagination. He theorized that Martians had built the canals to transport water from the polar ice caps to arid regions, a feat of engineering that spoke to their ingenuity and desperation. Lowell's ideas were met with skepticism by many scientists, but they resonated with the public. The notion of Martians, struggling to survive on a dying planet, became a fixture in popular culture. Writers like H. Wells and Edgar Rice Burroughs drew on these ideas to craft iconic works of science fiction, from The War of the Worlds to the Barsoom series. Mars became a stage for exploring humanity's fears and aspirations, a mirror reflecting our own struggles with survival and progress. As telescopes improved in the early 20th century, the canal theory began to unravel. Astronomers like E.M. Antoniadi used more powerful instruments to observe Mars and found no evidence of canals. Instead, they saw irregular surface features that had been misinterpreted as linear structures. The canals, it seemed, were an optical illusion, a trick of the eye caused by low-resolution images and the human brain's tendency to connect dots into patterns. By the mid-20th century, the scientific consensus was clear. There were no Martian canals, and the dream of an advanced civilization on Mars was replaced by the sobering reality of a barren desert. Despite this setback, Mars continued to inspire speculation about life. The discovery of polar ice caps and seasonal color changes on the planet's surface suggested that Mars might still be active, with water playing a role in its climate. Some scientists hypothesized that microbial life could exist in subsurface reservoirs or in pockets of liquid brine beneath the polar ice. These ideas gained new traction with the advent of space exploration, which offered the first direct glimpses of Mars. The 1960s and 1970s marked a turning point in our understanding of Mars as spacecraft began to replace telescopes as the primary tool for observation. The Mariner 4 mission in 1965 provided humanity's first close-up images of Mars, revealing a cratered and desolate landscape. These images were a stark contrast to the fertile world imagined by Lowell and his contemporaries. Subsequent missions, including the Viking landers of the 1970s, confirmed that Mars was a harsh, arid planet with no signs of intelligent life or lush vegetation. The Viking missions conducted life detection experiments, but the results were inconclusive, fueling debate about whether Mars might still harbor microbial life. While the dream of finding intelligent Martians faded, the possibility of microbial life remained an open question. Mars's surface conditions, cold, dry, and bombarded by radiation, are inhospitable to most known life forms, but its past tells a different story. Evidence of ancient riverbeds, lake beds, and mineral deposits suggests that Mars was once much more Earth-like, with a thicker atmosphere and abundant liquid water. If life ever arose on Mars, it may have persisted underground, protected from the harsh surface environment. The misconceptions of the past, from Martian gods to canal-building civilizations, may seem quaint or misguided in hindsight. Yet, they played a vital role in shaping humanity's relationship with Mars. These ideas fueled public interest and inspired generations of scientists, engineers, and storytellers to dream of imagination and evolve through observation, experimentation, and discovery. Today, our understanding of Mars is more accurate and nuanced than ever before, but the allure of the unknown remains. Mars still holds mysteries, from the possibility of subsurface life to the question of why its climate changed so dramatically. The history of misconceptions about Mars is a testament to our enduring curiosity, a reminder that our desire to understand the universe is as much about asking questions as it is about finding answers. As we look to the future of Mars exploration, we can celebrate the progress we've made while acknowledging the creative errors of the past. Misconceptions, after all, are part of the scientific process. They push us to test our ideas, challenge our assumptions, and refine our understanding of the cosmos. Mars, with its long history of inspiring myths and misconceptions, remains a beacon of possibility. A planet that invites us to dream, discover, and imagine what lies beyond the horizon. Landing on Mars is one of the most daunting challenges in space exploration. For engineers and scientists, it is a delicate ballet of precision and timing. A spacecraft traveling at tens of thousands of kilometers per hour must slow down, navigate Mars's thin and unpredictable atmosphere, and make a gentle touchdown on an alien surface, all without human intervention. The moments leading up to this critical event are among the most nerve-wracking in any mission, known as the 7 minutes of terror. This period encapsulates the extraordinary complexity, risk, and triumph of landing on Mars. The term was first popularized during NASA's Curiosity rover landing in 2012, but it has since become a universal descriptor for the tense descent phase of all Mars missions. The name captures the harrowing reality. In the 7 minutes it takes for a spacecraft to descend through Mars's atmosphere and reach the ground, mission control on Earth can do nothing but wait. At a distance of over 200 million kilometers, radio signals take approximately 14 minutes to travel from Mars to Earth, making real-time communication impossible. By the time the spacecraft sends word that it has entered the atmosphere, it has already landed, or crashed. The process begins as the spacecraft approaches Mars, hurtling toward the planet at speeds exceeding 200 kilometers per hour. At these velocities, even the slightest miscalculation can mean disaster. The spacecraft must hit the atmosphere at the correct angle. Too shallow and it will skip off into space. Too steep and it will burn up from the heat of entry. Precision is everything, and this moment marks the point of no return. As the spacecraft enters the atmosphere, the temperature around it skyrockets. Friction with the thin Martian air generates intense heat, reaching temperatures of up to 1600 degrees Celsius. To protect the payload, the spacecraft is equipped with a heat shield, a critical barrier designed to absorb and dissipate the searing energy. The fiery descent creates a plasma cloud around the spacecraft, temporarily blocking communication with mission control. This is the first of many aha moments of silence that amplify the tension back on Earth. Once through the upper atmosphere, the spacecraft faces its next challenge: deceleration. Mars's atmosphere is much thinner than Earth's, just 1% of the atmospheric pressure at sea level, which means it provides far less resistance to slow the spacecraft. To compensate, engineers deploy a massive supersonic parachute, often made of advanced materials capable of withstanding the incredible forces generated at speeds over Mach 2. The parachute slows the spacecraft to a fraction of its original velocity, but even this is not enough for a safe landing. At this stage, the heat shield is jettisoned, revealing the lander or rover inside. As the spacecraft descends, it uses radar to scan the terrain below, searching for a suitable landing site. This autonomous process, known as terrain relative navigation, compares the radar data to preloaded maps of the Martian surface, enabling the spacecraft to avoid hazards like boulders and craters. This technology was crucial for missions like Perseverance, which landed in Jezero Crater, a region filled with ancient riverbeds and rugged terrain. For larger payloads, such as rovers, the final phase of descent involves an innovative solution: the sky crane system. First introduced with the Curiosity rover, the sky crane is a marvel of engineering. As the spacecraft nears the surface, rocket-powered thrusters fire to slow its descent further. At an altitude of about 20 meters, The rover is lowered on nylon cables from a hovering platform. This delicate maneuver ensures that the rover touches down gently, minimizing the risk of damage. Once the rover is safely on the ground, the cables are severed, and the sky crane flies away to crash at a safe distance. The success of this intricate sequence depends on thousands of variables, each of which must perform flawlessly. From the timing of the parachute deployment to the precision of the sky crane's thrusters, every component is essential. And because Mars missions take years to plan and execute, there is no margin for error. A single failure during these 7 minutes can mean the loss of billions of dollars, years of work, and countless scientific opportunities. Despite the risks, humanity has achieved remarkable success in landing on Mars. The Viking landers in the 1970s were the first to demonstrate the feasibility of soft landings, while later missions, such as Pathfinder, Spirit, and Opportunity, refined the technology. The Sky Crane system, used for Curiosity and Perseverance, represents the pinnacle of innovation, enabling heavier and more sophisticated rovers to explore the Martian surface. The tension of the 7 minutes of terror is not confined to mission control. The event has captured the public imagination, becoming a symbol of human ingenuity and determination. Live broadcasts of Mars landings have drawn millions of viewers who share in the collective anticipation, anxiety, and elation as the final moments unfold. When a mission succeeds, the relief and joy are palpable, a testament to the countless hours of work and dedication behind each achievement. But these 7 minutes are more than a technical challenge. They are a reminder of the stakes involved in exploration. Landing on Mars is a leap into the unknown, a test of humanity's ability to solve problems and push the boundaries of what is possible. Each successful landing brings us closer to understanding the red planet and lays the groundwork for future missions, including the first human expeditions. As we look ahead to the next generation of Mars missions, the 7 minutes of terror will remain a defining feature of planetary exploration. Whether it is delivering new rovers, sample return capsules, or even human habitats, the challenge of landing on Mars will continue to inspire awe and admiration. It is a moment that encapsulates the spirit of exploration, a blend of risk, reward, and the relentless pursuit of knowledge. Mars, with its thin atmosphere and rugged surface, does not make landing easy, but these challenges only underscore the significance of each success. The 7 minutes of terror is a testament to what we can achieve when we dream big, work together, and dare to reach for the stars. Mars is a world of mysteries, a place where questions about life, water, and planetary history linger in every rock and ridge. To uncover its secrets, scientists have developed instruments of extraordinary sophistication, tools capable of peering beneath the surface, analyzing the atmosphere, and even sniffing up the faintest traces of organic compounds. These advanced instruments, carried aboard orbiters, landers, and rovers, have transformed Mars from a distant enigma into a planet that we can study with astonishing precision. They represent the pinnacle of human ingenuity, enabling us to explore a world millions of kilometers away without ever setting foot on its surface. One of the most iconic examples of advanced instrumentation is the suite of tools aboard the Curiosity rover, which landed in Gale Crater in 2012. At its heart is the Sample Analysis at Mars SAM instrument, a miniature chemistry lab housed within the rover's body. SAM is designed to analyze the composition of Martian soil, rocks, and air, searching for organic molecules that could indicate the building blocks of life. Using techniques like gas chromatography and mass spectrometry, SAM can identify complex chemicals and isotopes, providing insights into Mars's ancient environment and its potential for habitability. SAM's findings have revealed tantalizing evidence of organic molecules and seasonal variations in methane levels, with some exceptions were inspired by possible molting processes. Another groundbreaking instrument on Curiosity is the ChemCam, which combines a laser-induced breakdown spectrometer with a high-resolution camera. ChemCam's laser fires pulses at rocks up to 7 meters away, vaporizing tiny amounts of material. The resulting plasma emits light that is analyzed to determine the rock's elemental composition. This non-invasive technique allows scientists to study the geology of Mars with unparalleled detail, helping to reconstruct the planet's history of water and volcanic activity. Building on the successes of Curiosity, NASA's Perseverance rover, which landed in Jezero Crater in 2021, carries an even more advanced set of instruments. Among them is the PIXL, Planetary Instrument for X-ray Lithochemistry system, a tool that uses X-rays to map the elemental composition of rocks and soil at microscopic scales. PIXL's precision allows scientists to identify patterns that could point to ancient microbial life, such as the presence of biosignatures or textures indicative of biological activity. Working alongside PIXL is ShearLock, scanning habitable environments with Raman and luminescence, which uses ultraviolet light to detect organic compounds and analyze the mineralogy of rocks. ShearLock's laser also creates detailed maps of its target surfaces, guiding researchers to the most promising areas for study. Perseverance's suite of instruments is not limited to searching for signs of life. The rover also carries MOXIE. MOX alpha sanding is the proving science's use. The smaller amount of matters that reciprocate in the atmosphere, practically considers inexpensive, an experimental device that demonstrates the potential to produce oxygen from Mars's carbon dioxide-rich atmosphere. MOX's success in generating small amounts of breathable oxygen is a critical step toward enabling future human missions, proving that local resources can be used to support life and fuel production. This innovation highlights how advanced instruments are not only tools for science, but also key technologies for survival. The ingenuity of advanced instrumentation is not confined to rovers. Orbiters, like the Mars Reconnaissance Orbiter and the European Space Agency's Mars Express, carry powerful instruments that provide a global perspective on the planet. MRO's HiRISE Experiencer camera, for example, captures stunning images of the Martian surface with a resolution of up to 25 centimeters per pixel. These images have revealed features as small as individual boulders, offering new insights into the planet's geology and guiding the selection of landing sites for future missions. Another essential tool aboard MRO is the SHARAD, Shallow Radar Instrument, which uses radar waves to penetrate the surface and detect subsurface layers. SHARAD has been instrumental in mapping buried ice deposits, showing that Mars holds vast reserves of frozen water just beneath its dusty exterior. These findings have profound implications for both science and exploration, as they point to potential resources for future missions, while shedding light on Mars's climatic history. The European Space Agency's Trace Gas Orbiter, TGO, part of the ExoMars program, has taken the search for atmospheric clues to new heights. TGO is equipped with spectrometers that measure the composition of Mars's thin atmosphere, focusing on trace gases like methane and water vapor. Methane is of particular interest because it is often associated with biological activity on Earth, though it can also result from geological processes. GEO's precise measurements aim to determine the source of Martian methane, providing critical context for the methane fluctuations detected by Curiosity and other missions. One of the most revolutionary instruments in Martian exploration is Ingenuity, the small helicopter that flew alongside Perseverance. While not a traditional scientific instrument, Ingenuity represents a technological leap forward, demonstrating the feasibility of powered flight on Mars. Its onboard cameras and sensors have provided aerial perspectives of the Martian terrain, capturing breathtaking views of the planet's surface. Ingenuity's success has opened the door for future aerial explorers, which could carry advanced instruments to areas inaccessible to rovers or landers. The pursuit of advanced instrumentation continues to evolve, with upcoming missions promising even greater capabilities. The European Space Agency's Rosalind Franklin rover, part of the ExoMars program, will carry a drill capable of penetrating 2 meters below the surface, reaching layers that may have been shielded from radiation and preserved traces of life. Meanwhile, NASA's Mars Sample Return mission aims to retrieve the samples collected by Perseverance and bring them back to Earth for detailed analysis, using tools far more sophisticated than those that can be sent to Mars. The development of these instruments is a testament to human creativity and determination. Each tool is a carefully engineered marvel designed to withstand the harsh conditions of space travel and the Martian environment. Together, they form a collective effort to unlock the secrets of a distant world, answering questions that have intrigued humanity for centuries. Advanced instrumentation is more than just a collection of high-tech gadgets. It is the bridge between Earth and Mars, allowing us to study a planet millions of kilometers away with extraordinary precision. These tools are the eyes, ears, and hands of humanity on Mars, extending our reach and expanding our knowledge. As we continue to explore the Red Planet, the instruments we build will become even more sophisticated, enabling new discoveries and paving the way for the next great era of exploration. On April 19, 2021, history was made on Mars. A small, lightweight helicopter named Ingenuity lifted off the ground, hovered briefly in the thin Martian atmosphere, and then gently landed. It may have been a simple flight, lasting only 39.1 seconds, but its significance was monumental. Ingenuity became the first powered aircraft to fly on another planet. This technological achievement, years in the making, opened a new chapter in space exploration, demonstrating that flight was not only possible on Mars, but could also revolutionize the way we explore its rugged terrain. Ingenuity's journey to Mars began as a bold experiment. Initially conceived as a proof of concept, the helicopter's primary goal was to demonstrate that controlled, powered flight could work in an atmosphere as thin as Mars's, which is just 1% the density of Earth's. This challenge required ingenious engineering solutions. Ingenuity's twin rotors, each spanning 1.2 meters, were designed to spin at an astonishing 2,400 revolutions per minute, much faster than typical helicopter blades on Earth. This high speed generated the lift needed to overcome the planet's low atmospheric pressure. The helicopter's compact design reflected the constraints of interplanetary travel. Weighing only 1.8 kilograms, Ingenuity needed to be lightweight yet durable, with a body the size of a tissue box. Its power system relied on solar panels, which recharged its lithium-ion batteries to support its brief lifetime. Autonomous navigation was another critical feature, as the 14-minute communication delay between Mars and Earth meant Ingenuity had to fly without real-time input from mission control. Equipped with cameras and sensors, it could analyze its surroundings, stabilize itself, and safely land on its own. Ingenuity arrived on Mars aboard the Perseverance rover, tucked beneath the rover's chassis for the journey. Once Perseverance reached its landing site in Jezero Crater, Ingenuity was deployed onto the Martian surface, where it spent several days charging its batteries and undergoing system checks. The first flight, carefully planned and executed, was a triumphant moment not just for the mission team, but for humanity's exploration of the Red Planet. For the first time, a machine built on Earth had achieved powered flight in the skies of another world. What began as a technology demonstration soon evolved into a critical asset for Perseverance's mission. Ingenuity's initial flight was followed by a series of increasingly ambitious sorties, each one testing its capabilities and expanding its role. The helicopter's agility and aerial perspective allowed it to scout terrain that was difficult for Perseverance to navigate, identify potential hazards, and map the best routes for the rover. By flying ahead and capturing high-resolution images of the landscape, Ingenuity became the rover's aerial scout, a role that saved time and reduced risk. One of Ingenuity's most valuable contributions was its ability to explore areas that were otherwise inaccessible to ground-based rovers. Jezero Crater, an ancient lakebed with a rich geological history, is filled with rugged terrain, steep slopes, and scattered boulders. While Perseverance's design allows it to traverse many obstacles, there are limits to where it can safely go. Ingenuity, with its aerial mobility, offered a way to bridge this gap. Its flights provided detailed imagery of features such as river deltas, sedimentary layers, and potential sampling sites, offering insights that would have been impossible to obtain from the ground alone. Ingenuity's success has redefined what is possible in planetary exploration. Its flights have proven that aerial vehicles can play a vital role in studying Mars, complementing the capabilities of orbiters and rovers. While orbiters provide a global view of the planet and rovers offer detailed analysis at ground level, helicopters like Ingenuity fill the intermediate gap, providing high-resolution images and data over local areas. This three-tiered approach enhances our ability to understand Mars's complex geology and history. The implications of Ingenuity's success extend far beyond Mars. By demonstrating the feasibility of flight in a low-pressure environment, Ingenuity has paved the way for future aerial explorers on other worlds. For example, NASA's Dragonfly mission, set to launch in the late 2020s, will use a rotocraft to explore the dense atmosphere of Titan, Saturn's largest moon. Ingenuity's design and operational lessons have also informed plans for more advanced helicopters on Mars, which could carry scientific instruments to study the surface in greater detail or even transport small payloads between sites. Ingenuity's achievements are not just technical, but also symbolic. Its name, chosen by a high school student during a nationwide contest, reflects the creativity and determination that define humanity's exploration of space. The sight of Ingenuity hovering above the Martian surface, its shadow dancing across the ground, is a testament to what is possible when bold ideas are combined with meticulous engineering. Beyond its immediate contributions to the Perseverance mission, Ingenuity has captured the imagination of people around the world. Its flights, recorded in stunning detail by Perseverance's cameras, have provided a bird's-eye view of Mars like never before. These images, paired with the knowledge that they were captured by a flying machine millions of kilometers away, have produced a sense of wonder and possibility. Ingenuity reminds us that even in the harshest environments, innovation can unlock new frontiers. The helicopter's journey is far from over. Initially planned for just 5 test flights, Ingenuity has far exceeded expectations, completing dozens of sorties and continuing to operate well beyond its intended lifespan. Each new flight is an opportunity to push the boundaries of what it can achieve, whether by exploring more challenging terrain, flying longer distances, or capturing more detailed data. Ingenuity's resilience and adaptability are a testament to the ingenuity of its creators and the enduring spirit of exploration. Ingenuity's role in Mars exploration marks the beginning of a new era. It has demonstrated that flight is not just possible but practical on other planets, offering a glimpse of what future missions could achieve. As humanity continues its journey to understand Mars and prepare for eventual human missions, the lessons learned from Ingenuity will guide the way, showing us how to navigate the skies of an alien world. Bringing a piece of Mars back to Earth has long been one of the most ambitious goals in planetary exploration. While robotic missions have provided incredible insights into the red planet, there is a limit to what can be analyzed with instruments small enough to fit on a spacecraft. A sample return mission would bridge this gap, allowing scientists to study Martian rocks and soil with the full arsenal of Earth-based laboratories. It is a mission of unparalleled complexity, requiring international collaboration, cutting-edge technology, and years of meticulous planning. If successful, it could unlock the deepest secrets of Mars, from its geological history to the tantalizing possibility of past life. The groundwork for a sample return mission is already being laid. NASA's Perseverance rover, which landed in Jezero crater in 2021, is at the heart of this effort. One of its primary objectives is to collect and store samples of Martian rock and regolith, carefully chosen from locations that are likely to preserve evidence of ancient life or reveal critical details about Mars's past climate. Jezero crater was selected as the landing site because it was once a lake fed by a river, with a well-preserved delta that could contain organic materials and biosignatures. The samples Perseverance gathers are not just random scoops of soil. They are hand-picked by scientists for their potential to answer some of the most profound questions about Mars. The process of collecting these samples is a marvel of engineering and precision. Perseverance is equipped with a sophisticated drill mounted on its robotic arm, capable of extracting cores of rock about the size of a piece of chalk. Each core is sealed inside a titanium tube designed to preserve its pristine condition during the long journey back to Earth. The rover carries dozens of these tubes, and its mission includes carefully documenting the context of each sample, such as its exact location and surrounding geology. This information is critical for interpreting the data once the samples are analyzed on Earth. As of now, Perseverance has already begun filling its cache with a diverse array of samples. These include rock cores from ancient lake beds, sediment deposits from the delta, and materials that might contain traces of organic compounds. Some of the samples are from areas that show clear evidence of interaction with water, while others are from volcanic rock that can be precisely dated to provide a timeline of Mars's geological history. By collecting a variety of materials, the mission ensures a comprehensive snapshot of Jezero crater's environment. However, collecting the samples is only the first step in a mission that spans multiple spacecraft and several years. The next phase is retrieving the samples and sending them back to Earth, a challenge that has never been attempted in planetary exploration. NASA, in collaboration with the European Space Agency, ESA, has devised an ambitious plan to accomplish this. The Mars Sample Return Campaign involves a series of interconnected missions, each playing a critical role in transporting the samples across millions of kilometers of space. The first key step is the Sample Retrieval Lander, a spacecraft scheduled to launch in the late 2020s. This lander will carry a small rocket known as the Mars Ascent Vehicle, MAV, and a pair of sample-fitting helicopters based on the design of Ingenuity. Once on Mars, the lander will deploy the helicopters to locate and retrieve the sealed sample tubes left behind by Perseverance. Alternatively, if Perseverance is still operational, it may deliver the samples directly to the map. These helicopters, equipped with robotic grippers, will navigate the terrain autonomously, retrieving the samples with precision and returning them to the lander. Once the samples are secured, they will be loaded onto the Mars Ascent Vehicle, marking a historic first: the launch of a rocket from the surface of another planet. The MAV will carry the sample container into Mars orbit, where it will rendezvous with an ESA-built spacecraft called the Earth Return Orbiter. This spacecraft will capture the sample container, securely store it, and begin the long journey back to Earth. The final stage of the mission is the Earth Entry System, a specially designed capsule that will bring the samples safely through Earth's atmosphere. This capsule must be robust enough to withstand the intense heat and pressure of re-entry, while ensuring that the Martian materials remain uncontaminated by Earth's environment. Once the capsule lands, likely in a remote desert location, it will be retrieved by a team of scientists and transported to a high-security laboratory for analysis. The scientific potential of these samples is immense. Unlike the limited instruments on rovers, Earth-based laboratories can perform a wide range of analyses, from isotope dating and mineralogy to the search for organic molecules and potential biosignatures. These studies could confirm whether Mars once supported life, reveal how its climate evolved over billions of years, and provide insight into the processes that shaped the surface. The samples could also contain clues about Mars's interior, such as the composition of its mantle and core, offering a deeper understanding of its geology. A successful sample return mission would not only revolutionize Mars science, but also set a precedent for future exploration. It would demonstrate the feasibility of complex, multi-phase missions involving both robotic and human elements. The technologies developed for Mars sample return could be adapted for missions to other destinations, such as bringing back material from Europa's icy crust or Titan's organic-rich surface. The mission also carries symbolic significance. Bringing Martian material to Earth represents a milestone in humanity's journey to understand our place in the cosmos. It is the culmination of decades of exploration, from the early flybys of the Mariner missions to the groundbreaking discoveries of rovers like Spirit, Opportunity, Curiosity, and Perseverance. Each of these missions has contributed to a collective effort, building the knowledge and technology needed to make sample return possible. The challenges of the Mars sample return mission are daunting, but the rewards are unparalleled. It is a mission that combines the best of human creativity, collaboration, and determination, pushing the boundaries of what is possible in space exploration. As the pieces of this grand puzzle come together, the prospect of holding a piece of Mars in our hands grows closer to reality. When that day comes, it will mark not just a triumph of science and engineering, but a defining moment in humanity's quest to explore the unknown. The dream of sending humans to Mars is one of the most ambitious goals in the history of space exploration. Unlike robotic missions, human exploration has the potential to fundamentally change our understanding of the red planet. Astronauts on Mars could make real-time decisions, conduct complex experiments, and adapt to unforeseen challenges in ways no robot can match. But this dream requires overcoming immense challenges and preparing astronauts for the unique demands of living and working on an alien world. One of the first steps is understanding Mars's environment. Its atmosphere, composed mostly of carbon dioxide, is too thin to provide pressure or protection from radiation. Surface temperatures range from 20 degrees Celsius during the day to 125 degrees Celsius at night, and massive dust storms can last for weeks. To prepare, scientists use analog sites on Earth, such as Antarctica and the Atacama Desert, to test technologies and train crews in isolation and resource-limited conditions. Sustainable life support systems are critical. Astronauts on Mars will need to recycle air, water, and waste, much like systems tested on the International Space Station. Technologies that extract oxygen from carbon dioxide or recycle water from waste are being refined for Mars. Food production is another challenge. Transporting food for a multi-year mission is impractical, so astronauts will need to grow crops using methods like hydroponics and aeroponics. Researchers are even experimenting with using Martian regolith as a growing medium by enriching it with nutrients. Mars's low gravity, at 38% of Earth's, poses risks to human health, including muscle and bone loss. Data from space missions informs countermeasures, such as exercise routines and potential medical treatments. Radiation exposure, a major concern, requires habitats to be built underground or shielded with Martian regolith. Wearable protective gear and advanced materials are also being developed. Reliable energy sources are essential. While solar power is effective, frequent dust storms limit its reliability. Nuclear energy, such as NASA's kilopower reactor, offers a consistent alternative to power habitats, vehicles, and equipment. Combining multiple sources ensures resilience in Mars's unpredictable conditions. Psychological readiness is equally important. Astronauts face long periods of isolation and communication delays of up to 22 minutes round trip. Crews must operate autonomously, making decisions without real-time input from Earth. Strategies include selecting crews with strong interpersonal skills, simulating Earth-like environments through virtual reality, and ensuring access to mental health support. Technology plays a central role in preparation. Perseverance's MOXIE instrument has demonstrated the ability to produce oxygen from carbon dioxide, a vital step for future human missions. Ingenuity has shown that powered flight is feasible, paving the way for aerial vehicles to assist exploration. Advanced habitats, ranging from inflatable modules to 3D printed structures made of Martian regolith, are being developed to sustain life on the surface. The journey to Mars itself is a challenge. Spacecraft must protect crews from radiation and provide necessities for a multi-month voyage. Concepts include spinning modules for artificial gravity, advanced propulsion to shorten travel times, and robust shielding against cosmic rays. Each step in mission planning pushes the boundaries of human ingenuity, bringing us closer to the dream of walking on Mars. Mars is more than a destination. It is a proving ground for humanity's future in space. The innovations we develop for Mars will not only enable survival on another planet, but also prepare us for even greater adventures. As we take these first steps toward becoming an interplanetary species, Mars challenges us to imagine a future where humanity's reach extends beyond the stars. Mars presents an array of challenges that test the limits of human engineering and creativity. The thin atmosphere, extreme temperatures, and vast distances require innovative solutions to make exploration and survival possible. Each technological hurdle is a puzzle that demands ingenuity, collaboration, and cutting-edge advancement. One of the greatest challenges is entry, descent, and landing at L. Mars's atmosphere, just 1% as dense as Earth's, complicates slowing down spacecraft. Parachutes alone cannot provide enough drag, and retropropulsion is necessary to control descent. The sky crane system, first used with Curiosity and Perseverance, is a remarkable solution for landing heavy payloads. Future missions aim to refine this technology, exploring inflatable heat shields and more precise landing techniques to accommodate larger spacecraft and human habitats. Radiation protection is another critical issue. Without a magnetic field or thick atmosphere, Mars exposes explorers to harmful cosmic rays and solar radiation. Engineers are developing habitats shielded by Martian regolith or built underground to mitigate these risks. Advanced materials, including lightweight composites and radiation-absorbing polymers, are being tested to protect astronauts during surface operations and the journey to and from Mars. Energy generation is essential for sustaining missions. While solar power is reliable during clear conditions, Mars's infamous dust storms can block sunlight for weeks. NASA's kilopower reactor offers a promising solution, providing consistent nuclear energy to power habitats, life support systems, and scientific equipment. Combining solar and nuclear power ensures redundancy and resilience. Life support systems must be highly efficient and sustainable. Technologies that recycle air, water, and waste are critical for reducing reliance on resupply missions. The MOXIE instrument on Perseverance has already demonstrated the ability to produce oxygen from carbon dioxide in Mars's atmosphere. Scaling up this technology will be vital for human survival, providing breathable air and fuel for return trips to Earth. Communication is another significant challenge. The vast distance between Mars and Earth results in delays of up to 22 minutes, requiring autonomous systems for decision-making. Artificial intelligence, AI, is being integrated into spacecraft and robotic systems, enabling them to respond to dynamic conditions and execute complex tasks without human intervention. These advancements will allow astronauts to focus on mission-critical activities while relying on intelligent systems for support. Mobility on Mars's rugged terrain is crucial for exploration. Rovers like Perseverance have set the standard, but future missions may include advanced vehicles designed for human use. Concepts for pressurized rovers and aerial drones are being developed to extend the range of exploration. Ingenuity, the first helicopter to fly on Mars, has proven that aerial vehicles can provide valuable scouting capabilities and access to hard-to-reach areas. Resource utilization is at the heart of long-term survival. Extracting water from Martian ice or regolith is a priority for supporting life and producing fuel. Technologies for in-situ resource utilization, ISRU, are being refined to enable the extraction and processing of these materials. Building infrastructure from Martian soil, such as 3D printed habitats, reduces the need to transport bulky supplies from Earth. Finally, the journey to Mars itself poses technological challenges. Advanced propulsion systems, such as nuclear thermal propulsion, are being explored to shorten travel times and reduce radiation exposure during transit. Spacecraft must also provide robust shielding, reliable life support, and adequate living space for crews on multi-month missions. Solving these technological challenges is not just about reaching Mars, it is about redefining what humanity can achieve. Each breakthrough brings us closer to becoming a multi-planetary species, demonstrating that even the most formidable obstacles can be overcome with innovation and determination. Mars's challenges are immense, but they inspire solutions that will shape the future of exploration and expand the frontiers of human possibility. Colonizing Mars is a concept that has captured humanity's imagination for generations. The idea of transforming the red planet into a second home for humanity raises profound questions about survival, adaptation, and the future of life beyond Earth. While colonization remains a long-term goal, the visions for creating a sustainable presence on Mars are ambitious, blending science, technology, and imagination. At the heart of Mars colonization is the establishment of permanent habitats. Initial settlements would likely rely on prefabricated modules transported from Earth, designed to provide pressurized living environments, radiation protection, and life support systems. Over time, these habitats could evolve into self-sustaining colonies using local resources. Technologies like 3D printing with Martian regolith could enable the construction of domes, tunnels, and even large cities, reducing reliance on costly Earth-based supplies. Energy is a cornerstone of any colony. Solar power, combined with nuclear reactors, could provide reliable energy for growing food, running life support systems, and powering transportation. Kilo-power reactors and large solar farms are key components of proposed energy solutions, ensuring that colonies can thrive even during prolonged dust storms. Food production will be essential for survival and self-sufficiency. Colonies may rely on hydroponic and aeroponic farming techniques, allowing crops to grow without traditional soil. Scientists are also exploring ways to enhance Martian regolith, removing toxic perchlorates and enriching it with nutrients. These advancements would make it possible to grow staple crops like potatoes, wheat, and leafy greens, providing a sustainable food source for settlers. Water is another critical resource. Subsurface ice and hydrated minerals on Mars offer promising sources of water, which can be extracted and purified using advanced drilling and filtration technologies. Beyond drinking and hygiene, water can be used to produce oxygen and hydrogen, supporting both life and fuel production for rockets. Terraforming Mars, or altering its environment to make it more Earth-like, is a bold and controversial vision for colonization. Proposals range from releasing greenhouse gases to warm the planet and thicken its atmosphere, to building vast mirrors to reflect sunlight onto the surface. While terraforming remains speculative and centuries away at best, it represents humanity's ultimate ambition to transform a barren world into a thriving ecosystem. Mars colonization also raises important ethical and societal questions. How will governance be structured on a new planet? Who will have the right to settle? And how will resources be shared? These issues must be addressed as humanity prepares to establish a presence on Mars, ensuring that exploration is conducted responsibly and equitably. Ultimately, Mars colonization is about more than survival. It is about creating a new chapter in human history. It is a testament to humanity's resilience and ingenuity, a bold step toward ensuring the continuity of life beyond Earth. As technology advances and our understanding of Mars deepens, the vision of a thriving colony on the red planet moves closer to reality. Mars challenges us to think beyond borders, beyond planets, and beyond limits, offering a glimpse of what humanity can achieve when we dare to dream. Terraforming Mars, the idea of transforming the red planet into a habitable world, has captured the imagination of scientists and dreamers alike. The concept involves altering Mars's environment to create conditions similar to Earth's, where humans could live without the need for pressurized suits or habitats. But is terraforming a realistic goal, or does it remain in the realm of science fiction? While the challenges are immense, the vision of turning Mars into a second Earth is a powerful driver of innovation and exploration. The first step in terraforming Mars would be warming the planet. Mars's thin atmosphere, composed mostly of carbon dioxide, provides little insulation, resulting in frigid surface temperatures that average 60 degrees Celsius. One proposed method to increase temperatures is releasing greenhouse gases into the atmosphere. These gases, such as methane or chlorofluorocarbons, CFCs, could trap heat and create a runaway greenhouse effect, similar to what occurs naturally in opposing degrees of Celsius. However, producing or transporting enough greenhouse gases for this process would require unprecedented engineering feats. Another approach involves melting Mars's polar ice caps, which contain frozen carbon dioxide and water. As the ice sublates into gas, it would thicken the atmosphere, raising pressure and temperatures. This could potentially restart a limited water cycle, with liquid water forming in low-lying areas. Large orbital mirrors have been suggested as a way to direct sunlight onto the poles, accelerating this process. However, the scale and energy requirements of such a project are immense, pushing the limits of current technology. Creating breathable air is another monumental challenge. While Mars's atmosphere contains carbon dioxide, the oxygen needed for human survival is virtually absent. Introducing plants or algae capable of photosynthesis has been proposed as a long-term solution. These organisms could convert carbon dioxide into oxygen, slowly transforming the atmosphere. Yet, Mars's low temperatures, high radiation levels, and lack of liquid water make sustaining life on its surface extremely difficult without significant advancements in biotechnology and environmental engineering. One of the biggest obstacles to terraforming is Mars's lack of a magnetic field. Without it, the planet is exposed to solar wind, which strips away atmospheric gases and hinders the ability to retain heat and pressure. Restoring Mars's magnetic field, perhaps through artificial means, such as placing a magnetic shield at a strategic point in space, has been proposed. However, such solutions are purely theoretical and would require technologies far beyond our current capabilities. The ethical implications of terraforming are equally significant. Altering an entire planet raises questions about humanity's responsibility as stewards of the cosmos. If microbial life exists on Mars, would terraforming destroy its ecosystem? Should Mars be preserved as a natural laboratory for scientific discovery, or is it humanity's right to reshape it for survival? These debates must be addressed as the idea of terraforming moves from imagination to potential reality. For now, terraforming Mars remains speculative. The technological, logistical, and ethical challenges are staggering, and any significant progress would likely take centuries. However, the pursuit of this vision drives innovation and encourages us to think on a planetary scale. Each step toward understanding Mars, from studying its climate history to developing sustainable life support systems, brings us closer to unlocking its potential. Terraforming Mars may be an audacious goal, but it embodies the spirit of exploration and the human drive to overcome the impossible. Whether or not it becomes a reality, the pursuit of transforming Mars pushes the boundaries of science and expands the possibilities for humanity's future among the stars. As humanity sets its sights on Mars, questions about ownership, governance, and responsibility are becoming increasingly urgent. Who has the right to explore, use, or settle on Mars? How do we ensure that the red planet is explored ethically and sustainably? These questions are at the heart of space law and governance, a field that must evolve to address the challenges of interplanetary exploration. Currently, space activities are governed by international agreements, the most notable being the Outer Space Treaty of 1967. Signed by over 100 countries, this treaty declares that outer space, including Mars, is the province of all humankind. It prohibits any nation from claiming sovereignty over celestial bodies and mandates that space exploration be conducted for the benefit of all. While the treaty provides a framework for peaceful exploration, it leaves many questions unanswered, particularly regarding private enterprises and resource utilization. One major gray area is the extraction and use of resources on Mars. Companies like SpaceX and Blue Origin envision a future where humans mine Martian ice for water, oxygen, and fuel, or extract materials from the regolith for construction. The Outer Space Treaty does not explicitly prohibit resource extraction, but it also does not provide clear guidelines on how these activities should be regulated. The 2015 U.S. Space Launch Competitiveness Act allows American companies to use resources from space, but its interpretation is controversial and not universally accepted. Another challenge is governance on Mars itself. If colonies are established, who will govern them? Will they fall under the jurisdiction of the country that launched them, or will Mars develop its own independent governance? Historical analogies, such as the colonization of new lands on Earth, highlight the potential for conflicts over jurisdiction and resource allocation. Mars presents an opportunity to rethink governance from the ground up, potentially creating systems that prioritize cooperation, sustainability, and equity. Protecting Mars's environment is another critical concern. International agreements like the Planetary Protection Policy aim to prevent contamination of celestial bodies by Earth-based microbes and vice versa. However, as human activity on Mars increases, balancing scientific preservation with resource use and settlement becomes more complex. Ethical questions arise. Should Mars's natural state be preserved, or do humanity's needs take precedence? If microbial life is discovered, how would that impact our approach to colonization? The ethical dimensions of space law extend beyond Mars. The concept of planetary stewardship suggests that humanity has a responsibility to explore responsibly, minimizing harm and ensuring that the benefits of exploration are shared. This philosophy challenges us to think not only about what we can do on Mars, but what we should do as explorers and caretakers of the universe. The future of space law and governance will require collaboration between nations, private entities, and international organizations. Developing new agreements that address the realities of Mars exploration, resource sharing, environmental protection, and governance will be crucial to ensuring that Mars remains a place of discovery and opportunity for all. As we step onto new worlds, we must carry with us principles of fairness, responsibility, and foresight, ensuring that humanity's interplanetary endeavors are a force for good. Mars may not belong to any one nation or entity, but it belongs to all of us as a symbol of exploration, unity, and the boundless potential of human ambition. The challenge of governing Mars is not just legal. It is a test of our ability to work together in the pursuit of a shared future among the stars. The prospect of Mars becoming humanity's second home is both thrilling and daunting. While Earth will always be our origin and cradle, the challenges it faces, from overpopulation to climate change, underscore the need to expand our presence beyond a single planet. Mars, with its similarities to Earth and its tantalizing promise of resources, represents the most feasible location for this monumental step in human history. Mars offers unique advantages as a potential second home. Its day, or sol, is remarkably similar to Earth's, lasting 24 hours and 37 minutes, which would make the adjustment easier for human circadian rhythms. The planet also has water, locked in its polar ice caps and beneath the surface, which could be extracted and used for drinking, agriculture, and fuel production. Its carbon dioxide-rich atmosphere, though thin, provides a foundation for generating oxygen and methane, essential for life support and energy. Establishing a self-sustaining human presence on Mars would require immense effort and innovation. Early missions would focus on creating robust habitats capable of protecting settlers from radiation, extreme temperatures, and dust storms. Over time, these outposts could evolve into colonies, using local resources to build infrastructure and grow food. Technologies like 3D printing with regolith and hydroponic farming systems would enable settlers to reduce reliance on supplies from Earth, fostering long-term survival. Mars colonization would also challenge humanity to create new societal models. A Martian society, isolated from Earth and dependent on cooperation for survival, might develop innovative governance systems that prioritize sustainability, equity, and collaboration. The unique environment of Mars could inspire a culture that values resourcefulness and unity, offering a fresh start for human civilization. Despite its potential, Mars as a second home is not without limitations. Its gravity, at 38% of Earth's, could have unknown long-term effects on human health, particularly for children born and raised on the planet. Radiation exposure, even with shielding, remains a significant challenge, as does the psychological toll of living in a confined, isolated environment far from Earth. Overcoming these obstacles will require decades of research, innovation, and adaptation. Mars is not just a backup plan. It is a stepping stone for humanity's future in space. A thriving colony on Mars would demonstrate our ability to survive and adapt beyond Earth, paving the way for exploration of more distant worlds. By expanding our reach, we reduce the risks of extinction from planetary-scale disasters and ensure the continuity of human life. The vision of Mars as humanity's second home is as much about the future as it is about the present. It challenges us to push the boundaries of science, technology, and imagination while confronting profound questions about who we are and what we value. Mars invites us to dream of a future where humanity thrives, not just on one planet, but among the stars. A future where the red planet becomes a beacon of hope, resilience, and boundless possibility. As humanity ventures further into space, the exploration of Mars presents not only scientific and technological challenges, but also profound ethical questions. How we approach the red planet will define not only the success of our missions, but also the values we carry into the cosmos. From the preservation of Martian environments, to the equitable sharing of resources and the treatment of potential life forms, the ethical implications of Mars exploration require careful consideration. One of the most pressing ethical questions is the preservation of Mars's natural state. Mars is a world untouched by human activity, its landscapes shaped solely by geological and climatic processes over billions of years. As we explore and potentially settle the planet, our activities, whether landing spacecraft, extracting resources, or building habitats, will inevitably alter its environment. This raises the critical question: what responsibility do we have to preserve Mars as it is? Some argue that Mars should remain a natural laboratory for scientific study, protected from contamination and large-scale human impact. Others contend that the planet's resources should be used to ensure humanity's survival and progress. Balancing these perspectives will be a key challenge as we move forward. The possibility of life on Mars adds another layer of complexity. If microbial life exists, perhaps hidden in subsurface water reservoirs or frozen within ancient permafrost, our actions could threaten its survival. The contamination of Martian ecosystems with Earth-based microbes, introduced by spacecraft or human presence, poses a significant risk. International guidelines, such as the Planetary Protection Policy, aim to minimize this risk. But as human activity on Mars increases, enforcing these standards will become more difficult. The discovery of life would also raise profound ethical questions. Do we have the right to interfere with or alter another planet's biosphere? Should the existence of life, no matter how simple, take precedence over human exploration and settlement? Beyond Mars itself, the ethical implications of exploration extend to humanity's broader responsibilities. The resources needed for Mars missions are immense, requiring billions of dollars, advanced materials, and energy. Critics argue that these resources could be better used to address urgent problems on Earth, such as poverty, climate change, and public health. Proponents of Mars exploration counter that the knowledge and technologies developed through space exploration often have far-reaching benefits for Earth, driving innovation and inspiring future generations. Navigating this tension requires a clear understanding of how Mars exploration can contribute to the well-being of humanity as a whole. The potential colonization of Mars also raises questions of equity and governance. Who gets to decide how Mars is explored, settled, and utilized? Historically, exploration on Earth has often led to exploitation, with powerful nations or entities claiming resources and land at the expense of others. Mars offers an opportunity to do things differently, fostering international collaboration and ensuring that the benefits of exploration are shared equitably. However, the involvement of private companies such as SpaceX and Blue Origin complicates this dynamic. While these companies bring innovation and resources to Mars exploration, Their activities must be aligned with global ethical standards to prevent conflicts and ensure fairness. Governance on Mars itself is another critical consideration. If human colonies are established, how will they be governed? Will they remain under the jurisdiction of the countries or corporations that founded them, or will Mars develop its own political systems? Could Mars become an independent entity with its own laws and culture, or would it remain a frontier shaped by Earth-based interests? These questions have no easy answers, but they must be addressed proactively to avoid repeating the mistakes of Earth's colonial history. The ethical implications of Mars exploration also touch on humanity's philosophical responsibilities. As we expand our presence in the cosmos, we are not just exploring new worlds, we are shaping humanity's legacy. Mars offers an opportunity to demonstrate that exploration can be conducted responsibly, with respect for both the planet and the potential life it may harbor. It challenges us to think not only about what we can achieve, but also about the values we uphold: curiosity, stewardship, and a commitment to leaving the universe better than we found it. Finally, the ethical challenges of Mars exploration highlight the importance of including diverse perspectives in decision-making. Scientists, ethicists, policymakers, and the public all have a stake in how humanity approaches Mars. Engaging in open and inclusive dialogue ensures that our choices reflect a wide range of values and priorities, making exploration a collective endeavor rather than a pursuit driven by a select few. The ethical implications of Mars exploration are as vast as the planet itself. They challenge us to think critically about our responsibilities as explorers, stewards, and citizens of the universe. As we take our first steps toward becoming a multi-planetary species, these questions remind us that the choices we make today will shape the future of humanity among the stars. Mars is not just a destination, it is a mirror, reflecting our values and aspirations as we reach for the unknown. Mars has long held a unique place in the human imagination. From ancient mythology to modern cinema, the red planet has inspired countless stories, theories, and artistic expressions. Its vivid red color, visible even to the naked eye, has made it a celestial focal point for cultures worldwide, while its mysterious surface and proximity to Earth have fueled speculation about alien life and the possibility of human settlement. The way Mars is portrayed in popular culture reflects not only our fascination with the planet, but also our hopes, fears, and evolving understanding of the universe. The earliest cultural depictions of Mars are rooted in mythology. To the Babylonians, Mars was Nergal, the god of war and pestilence, while the Greeks and Romans associated the planet with their respective war deities, Ares and Mars. Its fiery red appearance linked it to bloodshed and conflict, an image that persisted for centuries. These mythological associations gave Mars an aura of power and danger, a theme that would carry into later artistic and literary representations. The 19th and early 20th centuries marked a turning point in Mars's cultural significance, fueled by advances in astronomy and the rise of science fiction. Giovanni Schiaparelli's observation of canali on Mars in 1877, mistranslated as canals, sparked widespread speculation about intelligent life on the planet. Percival Lowell, an American astronomer, popularized the idea of a dying Martian civilization constructing canals to distribute water, inspiring a wave of fascination with the red planet. These theories found fertile ground in literature, with works like H. Wells's The War of the Worlds, 1898, imagining Martians as technologically advanced invaders of Earth. The theme of alien invasion became a cornerstone of Mars fiction. Orson Welles's 1938 radio adaptation of The War of the Worlds famously caused panic among listeners who believed the fictional Martian invasion was real. This portrayal of Mars as a source of danger mirrored anxieties of the time, from fears of technological dominance to the unknown threats lurking beyond our world. Other works, like Edgar Rice Burroughs' Barsoom series, took a more adventurous approach, depicting Mars as a fantastical world of romance, heroism, and exotic life forms. As space exploration advanced in the mid-20th century, Mars's portrayal in popular culture shifted. The barren landscapes revealed by early spacecraft like Mariner 4 dashed hopes of a thriving Martian civilization, but they also opened new avenues for storytelling. Films like The Martian Chronicles, 1980, based on Ray Bradbury's seminal work, explored themes of colonization, environmental destruction, and humanity's impact on alien worlds. Mars became a canvas for reflecting on human nature, grappling with questions of identity, survival, and the consequences of exploration. The late 20th and early 21st centuries saw Mars emerge as a central figure in blockbuster science fiction. Films like Total Recall, 1990, and Red Planet, 2003, combined speculative science with action-packed narratives, imagining humans colonizing and terraforming Mars while encountering unforeseen dangers. Meanwhile, the allure of realism inspired works like Andy Weir's The Martian, 2011, adapted into a critically acclaimed film in 2015. The story of astronaut Mark Watney's struggle to survive on Mars captivated audiences, with its detailed depiction of the planet and the ingenuity required to overcome its challenges. The Martian reignited public interest in Mars exploration, highlighting the resilience of human spirit and the power of science. Mars has also played a significant role in music, art, and gaming. Gustav Holst's The Planet Suite 1-9-14-19-16 begins with Mars, the bringer of war, capturing the planet's mythological and emotional resonance. In visual art, Mars is often depicted as both a place of mystery and opportunity. Video games like Doom and Surviving Mars allow players to explore and conquer the Red Planet, reflecting humanity's desire to test its limits and imagine life beyond Earth. In addition to entertainment, Mars has become a powerful symbol of hope and ambition. Elon Musk's SpaceX missions have popularized the idea of Mars as humanity's future home, blending science fiction with real-world aspirations. Public fascination with Mars missions, from NASA's rovers to plans for human exploration, has made the planet a touchstone for discussions about innovation, resilience, and the long-term survival of humanity. The portrayal of Mars in popular culture often mirrors societal trends and technological advances. In times of uncertainty, Mars serves as a symbol of danger or an escape from Earth's challenges. In moments of optimism, it represents a beacon of exploration and progress. As our understanding of Mars deepens, its cultural representations continue to evolve, blending imagination with science and reflecting humanity's enduring curiosity. Mars in popular culture is more than entertainment. It is a testament to the human spirit. It reminds us of our capacity to dream, to question, and to strive for the unknown. From ancient myths to modern cinema, the Red Planet has been a mirror of our aspirations, fears, and boundless creativity. As we move close to stepping onto Mars's surface, the stories we tell about it will shape not only how we see the planet, but also how we see ourselves in the universe. Mars stands at the frontier of human ambition, a destination that embodies both the challenges and possibilities of our species. As we grapple with Earth's pressing issues, climate change, resource depletion, and overpopulation, the exploration and settlement of Mars offer a vision of resilience and progress. The Red Planet is more than a scientific objective. It is a stage for humanity's next great leap, a proving ground for innovation and a foundation for a multi-planetary future. The journey to Mars symbolizes humanity's drive to overcome the impossible. Reaching the planet requires pushing the limits of technology, from advanced propulsion systems to life support and radiation shielding. These innovations are not only crucial for Mars exploration, but also have far-reaching benefits for life on Earth. Technologies developed for surviving Mars's harsh conditions, such as water purification, renewable energy systems, and sustainable agriculture, could address critical challenges on our home planet, fostering a more resilient and equitable future. Mars also represents an opportunity to expand the boundaries of human knowledge. Its ancient landscapes hold the secrets of planetary evolution, climate change, and the potential for life beyond Earth. By studying Mars, we gain a deeper understanding of our own planet's history and future. The search for life on Mars, whether extinct or extant, could answer one of humanity's most profound questions. Are we alone in the universe? A discovery of even microbial life would revolutionize biology, philosophy, and our understanding of life's possibilities across the cosmos. The prospect of colonizing Mars carries profound implications for the survival of humanity. Earth is vulnerable to natural disasters, climate shifts, and even cosmic events like asteroid impacts. Establishing a self-sustaining presence on Mars would provide a backup plan, ensuring the continuation of human civilization in the face of existential threats. A thriving Martian colony would also serve as a launchpad for exploring deeper into the solar system, from the moons of Jupiter to the icy worlds of the Kuiper Belt and beyond. Mars challenges us to think differently about governance, society, and culture. A Martian colony, isolated from Earth and dependent on cooperation for survival, could inspire new models of governance that prioritize sustainability, equity, and innovation. The unique conditions on Mars might foster a culture that values resourcefulness and unity, offering a fresh perspective on what it means to be human. Such a society would not only shape life on Mars, but also influence the way we approach challenges on Earth. Yet, the future of humanity on Mars is not without its challenges. Building a self-sufficient colony requires solutions to significant technical, physical, and ethical hurdles. From developing sustainable food systems to addressing the psychological effects of isolation and low gravity, the path to a thriving Martian society is fraught with obstacles. The ethical implications of transforming Mars's environment and utilizing its resources also demand careful consideration. How do we balance exploration and preservation? What responsibilities do we have as stewards of another planet? The vision of humanity on Mars also raises questions about identity and purpose. As we expand into the cosmos, what will it mean to be human? How will our connection to Earth evolve as we establish lives on other worlds? Mars invites us to rethink our place in the universe, to see ourselves not just as inhabitants of one planet, but as citizens of the cosmos. Mars and the future of humanity are intertwined in a story of hope and ambition. The red planet challenges us to confront our limits, to innovate, and to dream of a world where humanity thrives, not just on Earth, but among the stars. As we take our first steps toward becoming a multi-planetary species, Mars reminds us of the boundless potential of human ingenuity and the enduring spirit of exploration. The path to Mars is not just about science and technology. It is about defining the future of humanity. It is a journey that unites curiosity, creativity, and determination, pushing us to imagine a future where the impossible becomes possible. Mars is not the end of the journey, but the beginning of a new chapter in the story of humanity, a chapter that expands our horizons and redefines what it means to explore, adapt, and thrive. The quest to explore Mars is not just a challenge for individual nations or organizations. It is a shared endeavor that unites humanity in the pursuit of knowledge and progress. Mars exploration requires a level of collaboration that transcends borders. blending resources, expertise, and aspirations from around the world. As we aim to send humans to Mars and establish a sustainable presence, international cooperation becomes not only an opportunity but a necessity. Mars missions are inherently complex and costly, requiring decades of planning, cutting-edge technology, and significant financial investment. No single country, regardless of its technological or economic strength, can shoulder the burden alone. Collaborative projects like the International Space Station have already demonstrated the power of partnership in space exploration. Built and operated by a coalition of nations, the ISS serves as a model for how international collaboration can overcome technical and logistical challenges while fostering goodwill and shared success. Mars exploration has already benefited from global efforts. The European Space Agency, ESA, NASA, Russia's Roscosmos, India's ISRO, and others have contributed to Mars missions. From orbiters like ESA's Mars Express and India's Mars Orbiter mission to landers and rovers, each mission builds on the knowledge gained from its predecessors, creating a shared foundation of data and expertise. The ExoMars program, a collaboration between ESA and Roscosmos, highlights how pooling resources can lead to ambitious projects, such as drilling beneath Mars's surface to search for signs of life. Future missions, particularly those involving human exploration, will require even greater levels of collaboration. Developing the infrastructure to support human life on Mars, habitats, life support systems, energy sources, and transportation, demands contributions from diverse scientific and engineering disciplines. Countries with expertise in specific areas, such as robotics, materials science, or propulsion, can bring their strengths to the table, creating a network of innovation that accelerates progress. International collaboration also enhances the ethical and philosophical dimensions of Mars exploration. By involving multiple nations and cultures in decision-making, we can ensure that the benefits of exploration are shared equitably and that the mission reflects the values of humanity as a whole. This inclusive approach helps address critical questions about governance, resource allocation, and environmental protection, avoiding the pitfalls of competition and conflict that have historically accompanied exploration on Earth. Private industry also plays a pivotal role in Mars exploration, adding another layer of complexity to international collaboration. Companies like SpaceX, Blue Origin, and others bring innovation and funding to the table, but their goals may not always align with those of governments or international organizations. Coordinating efforts between public and private sectors is essential to ensure that Mars exploration remains focused on the collective good rather than narrow interests. The challenges of Mars demand a global perspective. For example, mitigating risks like radiation exposure, resource scarcity, and psychological stress requires expertise and innovation from multiple fields and nations. Collaborative research efforts, such as sharing data from Earth-based analog missions or conducting joint simulations, can provide valuable insights and solutions. Partnerships also reduce redundancy and effectively. Beyond the practical benefits, international collaboration in Mars exploration fosters unity and inspiration. Mars represents a shared goal that transcends political, cultural, and economic differences. It reminds us that, despite our divisions, humanity is capable of coming together to achieve extraordinary things. The image of astronauts from different nations standing side by side on Mars would symbolize a new era of cooperation, demonstrating that our greatest achievements are those we accomplish together. As humanity prepares to step onto the red planet, the role of international collaboration cannot be overstated. It is not just a matter of necessity, but a reflection of our values as a species. Mars challenges us to think beyond borders and to approach exploration as a shared journey, one that unites us in the pursuit of knowledge, resilience, and progress. Together, we can turn the dream of Mars into a reality, forging a path that inspires future generations and redefines what is possible for humanity. Exploring Mars has been a driving force behind some of the most significant advancements in space technology. The challenges of reaching, studying, and eventually settling on the red planet have pushed engineers and scientists to develop groundbreaking solutions that not only advance planetary exploration, but also have transformative applications here on Earth. From propulsion systems to robotics, the pursuit of Mars has shaped the evolution of space technology and will continue to do so for decades to come. One of the most significant areas of advancement has been spacecraft propulsion. Traveling to Mars requires navigating the vast distances of interplanetary space, where fuel efficiency and reliability are paramount. Traditional chemical rockets, while powerful, are limited in range and efficiency, spurring the development of alternative propulsion systems. Electric propulsion, such as ion and Hall-effect thrusters, has emerged as a key technology for robotic missions, offering greater fuel efficiency and extended mission lifespans. For human missions, concepts like nuclear thermal propulsion promise to drastically reduce travel times, mitigating the risks of prolonged exposure to cosmic radiation and microgravity. Landing on Mars has also driven technological innovation. The planet's thin atmosphere poses unique challenges, as it provides too little resistance for parachutes alone, yet enough to generate significant heat during entry. To address this, engineers have developed systems like the Sky Crane, used for Curiosity and Perseverance, which allows heavy payloads to be lowered gently to the surface. Future missions are exploring advanced techniques, such as inflatable heat shields and precision-guided descent systems, to enable the safe landing of larger spacecraft, including human habitats. Robotics has been at the forefront of Mars exploration, with rovers like Spirit, Opportunity, Curiosity, and Perseverance paving the way. These mobile laboratories are equipped with advanced instruments capable of analyzing rocks, soil, and atmospheric conditions with incredible precision. Autonomous navigation systems allow rovers to traverse complex terrain, making decisions in real time without waiting for instructions from Earth. Ingenuity, the first helicopter to achieve powered flight on another planet, represents a new frontier in aerial robotics, demonstrating the potential for exploring areas inaccessible to ground-based vehicles. The evolution of space technology for Mars has also spurred advancements in life support and habitat systems. Maintaining human life on Mars requires closed-loop systems that recycle air, water, and waste with minimal loss. Technologies tested on the International Space Station, such as water recovery systems and oxygen generation, are being adapted for use on Mars. Additionally, habitat designs are incorporating radiation shielding, thermal insulation, and modular construction, ensuring they can withstand Mars's extreme conditions while supporting long-term habitation. Energy systems have undergone significant innovation to meet the demands of Mars missions. Solar power, a mainstay of robotic missions, has been optimized for efficiency and durability, enabling rovers to operate in harsh conditions. For human exploration, nuclear power systems like NASA's kilopower reactor offer consistent energy even during prolonged dust storms that can obscure sunlight for weeks. Hybrid energy solutions combining solar and nuclear power are being developed to ensure redundancy and reliability. Mars exploration has also revolutionized materials science. Lightweight, durable materials capable of withstanding extreme temperatures, radiation, and abrasion have been developed for spacecraft rovers and habitats. Advanced composites, high-strength alloys, and radiation-resistant polymers are critical for both Mars missions and applications on Earth, from aerospace engineering to medical devices. Communication technologies have evolved to bridge the vast distance between Earth and Mars, where signals can take up to 22 minutes to travel one way, High-gain antennas, relay satellites, and laser communication systems are enabling faster and more reliable data transmission, critical for managing complex missions and ensuring astronaut safety. These innovations have implications far beyond safety, including global communication networks and data transmission on Earth. The pursuit of Mars has also accelerated advancements in artificial intelligence, AI, and automation. Rovers and orbiters rely on AI to process vast amounts of data, identify areas of interest, and make autonomous decisions. These technologies are being refined for human missions, where AI systems will assist with navigation, equipment maintenance, and health monitoring, reducing the cognitive load on astronauts and enhancing mission safety. Perhaps most importantly, Mars exploration drives innovation by fostering collaboration between nations, private companies, and research institutions. Programs like NASA's Artemis and ESA's ExoMars have brought together diverse expertise to tackle shared challenges, creating technologies that benefit humanity as a whole. The involvement of private companies like SpaceX and Blue Origin has further accelerated the pace of innovation, introducing cost-effective solutions and ambitious timelines for Mars exploration. The legacy of Mars-driven technology extends far beyond the red planet. Many of the advancements made for Mars missions have practical applications on Earth, from improving renewable energy systems to developing efficient water purification methods. The technologies that enable us to survive on Mars, where resources are scarce and the environment is unforgiving, are precisely the innovations needed to address global challenges like climate change and resource scarcity. Mars and the evolution of space technology are deeply interconnected. Each mission to the red planet pushes the boundaries of what is possible, inspiring new ideas and solutions that transform both space exploration and life on Earth. As we prepare for the next phase of Mars exploration, the technologies we develop will not only bring us closer to becoming a multi-planetary species, but also ensure a more sustainable and innovative future for humanity. As humanity ventures further into space, the psychological challenges of long-duration missions come into sharp focus. Traveling to Mars and establishing a human presence on the red planet require more than technological and physical readiness. They demand a deep understanding of how isolation, confinement, and the alien environment affect the human mind. The mental resilience of astronauts is as critical to mission success as the spacecraft carrying them. The journey to Mars is a psychological marathon. With current propulsion technology, the trip takes 6 to 9 months each way, during which astronauts will live in cramped quarters with limited privacy. The monotony of daily routines, the absence of natural environments, and the sheer distance from Earth create a sense of isolation that can weigh heavily on even the most experienced crew members. Communication delays of up to 22 minutes round trip mean that real-time conversations with family, friends, or mission control are impossible, amplifying feelings of disconnection. Once on Mars, the psychological challenges become even more pronounced. The planet's barren, lifeless landscapes offer no familiar cues to comfort the human mind. Astronauts will face extreme conditions, including frigid temperatures, relentless radiation, and the need to wear protective suits whenever venturing outside. The knowledge that help from Earth is months away, both in time and distance, creates an unparalleled sense of autonomy and vulnerability. Team dynamics play a pivotal role in overcoming these challenges. A mission to Mars will involve small, diverse crews working in close proximity for extended periods. The success of these missions depends on effective communication, conflict resolution, and cooperation under stress. Crew selection will prioritize individuals with exceptional interpersonal skills, adaptability, and emotional intelligence. Training programs simulate isolation and confinement, allowing crews to develop trust and teamwork before launch. NASA and other space agencies have conducted studies to better understand the psychological effects of long-duration space missions. The HESIA, High Space Exploration Analog and Simulation Program, for example, places volunteers in Mars-like habitats on Earth for months at a time to study how isolation impacts mental health and group dynamics. Participants report challenges such as interpersonal tensions, emotional fatigue, and the need for structured routines to maintain morale. These simulations provide valuable insights into the coping strategies that will be essential for Mars missions. Scattered across many pages of the volume are doubtless many stories. Technology plays a critical role in mitigating psychological stress. Virtual reality, VR, systems are being developed to simulate Earth-like environments, allowing astronauts to experience familiar sights and sounds, such as forests, oceans, or starry skies. These virtual assistants help counteract the sensory monotony of space travel and Mars's stark landscapes. Capable of providing mental health support and companionship are also being explored. These systems could monitor astronauts' well-being, offer personalized coping strategies, and provide interactive activities to reduce feelings of loneliness. The psychological toll of living on Mars extends beyond the immediate mission. Astronauts returning to Earth will need time to readjust, both physically and mentally. The experience of living on another planet, with its unique challenges and isolation, may have lasting effects on their perspective, relationships, and sense of identity. Programs to support astronauts' reintegration into life on Earth are as crucial as their pre-mission training. Despite these challenges, Mars exploration also offers profound psychological rewards. The opportunity to be part of one of humanity's most ambitious endeavors can provide a deep sense of purpose and accomplishment. The awe of standing on another planet, gazing at the Martian horizon, and contributing to scientific discovery can inspire a profound connection to the broader universe. Many astronauts report transformative experiences, often described as the overview of psych, where seeing Earth from space reshapes their understanding of humanity's place in the cosmos. Mars missions may evoke a similar sense of wonder, motivating astronauts to endure the hardships for the sake of exploration and progress. Addressing the psychological challenges of Mars exploration is not only about ensuring mission success, but also about safeguarding the well-being of the pioneers who will lead humanity into the cosmos. As we prepare for these missions, developing robust support systems, fostering strong team dynamics, and leveraging technology to create comfort and connection will be critical. The lessons learned will not only apply to Mars, but also inform future exploration of even more distant worlds. Mars challenges us to push the boundaries of human resilience, testing not just our technological capabilities, but also the strength of the human spirit. The journey will be difficult, but the rewards, both personal and collective, will be extraordinary. By understanding and addressing the psychological dimensions of Mars exploration, we can ensure that humanity's first steps on the red planet are not only a triumph of science and engineering, but also a testament to the indomitable will of the human mind. Mars has always been more than a planet. It is a symbol, a mirror, and a challenge that reflects humanity's deepest aspirations and questions. As the closest world to Earth with the potential to harbor life and support human settlement, Mars occupies a unique place in our cosmic story. Exploring Mars is not just about understanding its past or shaping its future. It is about defining what it means to be human in a vast and mysterious universe. From ancient myths to modern science, Mars has captured the human imagination. Its red glow, visible in the night sky, made it a figure of awe and speculation in early civilizations, often associated with war and power. As our understanding of Mars evolved, so too did its symbolic meaning. It became a canvas for imagining alien civilizations, a frontier for scientific discovery, and a destination for humanity's greatest ambitions. Today, Mars serves as a reminder of our potential to dream and achieve the extraordinary. Mars's role in shaping humanity's cosmic identity begins with the profound questions it raises. Did life ever exist on Mars? And if so, what does that tell us about the origins and prevalence of life in the universe? The search for life on Mars is not just a scientific pursuit. It is a philosophical journey that forces us to confront the possibility that Earth is not unique. If microbial life is discovered on Mars, it would confirm that life can arise independently on other worlds, reshaping our understanding of biology and our place in the cosmos. Alternatively, if Mars is found to be lifeless, despite having once been habitable, it underscores the fragility and rarity of life, emphasizing our responsibility to protect and cherish it. The exploration of Mars also challenges humanity to think about its future beyond Earth. For the first time in history, we have the tools and knowledge to consider becoming a multi-planetary species. This shift in perspective transforms how we see ourselves, not just as inhabitants of Earth, but as explorers of the cosmos. Mars offers a tangible step toward this vision, serving as a proving ground for the technologies, governance systems, and societal values needed to thrive on other worlds. It is a bridge between the familiar and the unknown, a place where humanity can test its capacity to adapt and endure. Mars's potential to support human settlement also raises profound questions about identity and culture. What kind of societies will we build on Mars? How will the unique challenges of life on the red planet shape the values, traditions, and relationships of its inhabitants? A Martian colony, isolated from Earth and reliant on collaboration for survival, might develop a distinct identity, reflecting the ingenuity and resilience of its pioneers. This new culture could influence humanity as a whole, offering fresh perspectives on cooperation, resourcefulness, and sustainability. The act of exploring Mars is itself a defining feature of our cosmic identity. It embodies the human drive to seek knowledge, overcome challenges, and push boundaries. Mars represents the ultimate test of this spirit, demanding innovation, courage, and perseverance. Each step we take on Mars, from landing rovers to envisioning human habitats, is a testament to humanity's ability to turn dreams into reality. Yet, Mars also invites reflection on our connection to Earth. As we study its ancient riverbeds, dried-up lakes, and lost atmosphere, we see a cautionary tale of planetary change. Mars shows us what can happen when a planet's environment becomes hostile to life, offering lessons that resonate deeply with the challenges we face on Earth. Exploring Mars reminds us of the delicate balance that sustains life and the importance of preserving our own planet, even as we look to others. Mars's role in humanity's cosmic identity extends beyond science and exploration. It is a source of inspiration, a reminder of our shared curiosity and potential. The stories we tell about Mars, in literature, art, and popular culture, reflect our hopes and fears, shaping how we imagine the future. These narratives connect us across generations, fueling a collective vision of what humanity can achieve. As we prepare to take our first steps on Mars, the red planet challenges us to think not only about where we are going, but also about who we are. It invites us to embrace our role as explorers and stewards, creators and preservers. Mars is not just a destination, it is a reflection of our highest aspirations and a reminder of the vast possibilities that lie before us. The journey to Mars is a journey of self-discovery, a chance to redefine what it means to be human in a universe filled with wonders. By exploring Mars, we are not only reaching for the stars, but also uncovering the essence of our cosmic identity, a story of curiosity, resilience, and the enduring spirit of exploration. The exploration of Mars is more than a series of scientific missions. It is a testament to humanity's enduring curiosity and determination. As we push the boundaries of knowledge and technology to understand the red planet, we are creating a legacy that will shape not only our understanding of Mars, but also our place in the cosmos. This legacy is a story of discovery, innovation, and inspiration, one that connects the achievements of the past with the possibilities of the future. The scientific legacy of Mars exploration is profound. Through decades of missions, from the early flybys of Mariner 4 to the sophisticated rovers and orbiters of today, we have transformed Mars from a distant point of light into a world rich with history and potential. These missions have revealed a planet once shaped by water, with ancient riverbeds, lakes, and deltas offering clues to its past habitability. The discovery of organic molecules and seasonal methane fluctuations has fueled the search for life, bringing us closer to answering one of humanity's most profound questions: are we alone? Mars exploration has also advanced our understanding of planetary evolution. By studying its geology, climate, and atmosphere, we have gained insights into the forces that shaped not only Mars, but also Earth and other worlds. The comparative study of Mars's climate history provides valuable lessons about planetary change, offering warnings and guidance for managing Earth's own environmental challenges. These scientific achievements are not just milestones, they are building blocks for future exploration, guiding our next steps on the red planet and beyond. The technological legacy of Mars exploration is equally significant. Each mission has pushed the boundaries of what is possible, driving innovation in robotics, materials science, propulsion, and more. The development of autonomous systems capable of navigating Mars's rugged terrain and conducting complex experiments has revolutionized our ability to explore remote environments. Innovations like the Sky Crane, used to land heavy payloads like the Curiosity and Perseverance rovers, have set new standards for planetary landings. These technologies not only enable exploration, but also inspire applications on Earth, from autonomous vehicles to renewable energy systems. Mars exploration has also left an indelible mark on human culture. The red planet has been a source of fascination for centuries, inspiring myths, stories, and scientific inquiry. Modern missions have brought Mars closer to the public imagination, with stunning images of its surface and detailed accounts of its exploration. These narratives connect people around the world, sparking curiosity and fostering a sense of shared achievement. The success of missions like Perseverance and Ingenuity demonstrates what humanity can achieve when we work together, serving as a reminder of our collective potential. Perhaps the most enduring legacy of Mars exploration is the inspiration it provides. The pursuit of Mars challenges us to dream bigger, think bolder, and strive for the extraordinary. It is a story of resilience and perseverance, of overcoming obstacles to achieve the seemingly impossible. Mars exploration reminds us that the boundaries of human potential are not fixed. They are defined by our willingness to push beyond them. Looking to the future, the legacy of Mars exploration will continue to grow. As we plan human missions to the red planet, the knowledge and technologies developed through decades of robotic exploration will guide our efforts. The first footprints on Mars will be the culmination of generations of work, a moment that honors the legacy of those who dared to ask questions and seek answers. These missions will not only expand our understanding of Mars, but also set the stage for exploring other worlds, from Europa's icy oceans to the distant moons of Saturn. Mars's legacy is not confined to science or technology. It is a reflection of humanity's spirit. It is a reminder that exploration is not just about reaching new places, but about discovering new possibilities within ourselves. By exploring Mars, we affirm our commitment to curiosity, innovation, and the pursuit of knowledge. We celebrate the shared human drive to explore, to adapt, and to thrive. As we stand on the cusp of a new era in Mars exploration, we are writing a legacy that will endure for generations. It is a legacy that connects the past with the future, a bridge between what we know and what we have yet to discover. Mars, with its ancient landscapes and uncharted possibilities, invites us to leave a mark, not just on its surface, but on the story of humanity. This legacy will inspire not only those who walk on Mars, but also those who dream of the stars, ensuring that the exploration of the red planet remains a defining chapter in the journey of humankind. Mars is more than the next frontier. It is a stepping stone to the cosmos. As humanity prepares to establish a sustainable presence on the red planet, Mars serves as a bridge between our home on Earth and the vast expanse of space. The lessons we learn from exploring and inhabiting Mars will shape the long-term future of exploration, setting the stage for humanity to reach deeper into the solar system and beyond. The immediate value of Mars lies in its challenges. The harsh environment, vast distance from Earth, and reliance on local resources push the limits of human ingenuity. Developing the technologies and strategies to survive on Mars, efficient life support systems, renewable energy sources, radiation protection, and self-sustaining habitats, will lay the groundwork for missions to more distant worlds. These advancements will not only enable survival on Mars, but also prepare us for the rigors of exploring moons like Europa, Titan, and Enceladus, which present even greater challenges. Mars is a testing ground for interplanetary governance and collaboration. The establishment of a colony on Mars will require new models of cooperation that balance the interests of nations, private companies, and humanity as a whole. These frameworks, developed on Mars, could serve as blueprints for managing future settlements on other celestial bodies. By fostering inclusive and equitable approaches to exploration, we can ensure that the expansion of humanity into space reflects our highest values. Mars's proximity and relative similarity to Earth make it an ideal candidate for long-term settlement. While it presents formidable obstacles, its abundance of resources, water, ice, carbon dioxide, and minerals, provides the foundation for a self-sufficient society. Establishing a thriving colony on Mars will demonstrate humanity's ability to adapt to alien environments, a skill that will be essential for exploring more extreme destinations, like the asteroid belt or the moons of the gas giants. The role of Mars in humanity's long-term exploration is not limited to its immediate vicinity. A sustainable presence on Mars could serve as a launchpad for missions deeper into the solar system. The planet's lower gravity and lack of a thick atmosphere make it an ideal location for constructing and launching spacecraft, significantly reducing the energy costs of interplanetary travel. Colonies on Mars could become hubs of innovation and exploration, driving humanity's expansion to the outer planets and beyond. Mars exploration also has profound implications for our understanding of life in the universe. By studying Mars's history and searching for signs of past or present life, we refine our criteria for identifying habitable environments on exoplanets. The techniques and instruments developed for Mars exploration can be adapted for missions to other celestial bodies, from Venus's cloud layers to the icy oceans of Europa and Ganymede. Mars is not just a destination, it is a proving ground for humanity's ability to seek life and knowledge wherever they may exist. The long-term future of exploration hinges on humanity's ability to innovate and inspire. Mars plays a central role in this process, challenging us to develop technologies that benefit both space exploration and life on Earth. The pursuit of Mars has already driven advancements in renewable energy, water recycling, robotics, and artificial intelligence, with applications far beyond the space sector. As we continue to explore Mars, these innovations will accelerate, shaping industries and improving quality of life worldwide. Mars also inspires a broader vision of humanity's place in the cosmos, yet invites us to think beyond immediate challenges and imagine a future where we are not bound to a single planet. The dream of a multi-planetary civilization is not just about survival. It is about thriving, about expanding the horizons of human experience and ensuring the continuity of our species across millennia. In the long term, Mars may become the first chapter in a much larger story. As we establish ourselves on the red planet, we will unlock the skills and knowledge needed to explore interstellar space. Concepts like generation ships, advanced propulsion systems, and self-sustaining habitats for deep space travel will build on the foundation laid by Mars exploration. The challenges we face on Mars will teach us how to overcome the obstacles of interstellar travel, transforming dreams of reaching other star systems into achievable goals. Mars and the long-term future of exploration are inextricably linked. The red planet is where humanity will take its first steps toward becoming a truly space-faring civilization, mastering the skills needed to survive and thrive beyond Earth. As we look to the stars, Mars will remain a symbol of what we can achieve when we dream boldly and work together. It is not just the next destination, it is the beginning of an endless journey, one that will define humanity's place in the universe for generations to come. Mars holds a unique place in the story of humanity. For centuries, it has been a source of wonder, curiosity, and inspiration, a celestial neighbor that feels simultaneously close and unreachable. Its fiery glow in the night sky has sparked myths and legends. Its mysterious canals have fueled speculation about alien life, and its stark, desolate beauty has beckoned us to explore its secrets. As we stand on the threshold of making Mars a tangible part of humanity's future, its allure remains as powerful as ever. The appeal of Mars begins with its familiarity. Among all the planets in the solar system, Mars is the one most like Earth. Its days, only slightly longer than ours, offer a sense of rhythm and normalcy. Its seasons, driven by a tilted axis, remind us of the cycles that define life on our home planet. Yet, for all its similarities, Mars is a world of profound contrasts, an alien landscape of red deserts, towering volcanoes, and deep canyons, shaped by forces that hint at both its violent past and its serene isolation. Mars's greatest appeal lies in its potential. It is a planet that invites discovery at every level, from the microscopic to the monumental. The search for life on Mars, whether in its distant past or hidden in its present, drives some of the most exciting scientific endeavors of our time. The possibility of uncovering evidence that Mars once harbored life, or still does, would be one of the most transformative discoveries in human history. It would confirm that life is not unique to Earth, opening new chapters in biology, philosophy, and our understanding of the universe. For humanity, Mars is a symbol of resilience and progress. Its challenges: thin atmosphere, freezing temperatures, radiation exposure, demanding radiation and ingenuity. Every rover that lands, every sample collected, and every system that supports human life there represents a triumph over these obstacles. Mars reminds us that the path to progress is rarely easy, but always rewarding, inspiring generations to look beyond what seems impossible. Mars also serves as a mirror, reflecting humanity's dreams and ambitions. It has been imagined as the home of advanced civilization, a site of cosmic conflict, and a frontier of survival and transformation. These stories, rooted in both science and fiction, have shaped how we think about exploration and our relationship with the unknown. As we move closer to stepping onto Mars, the narratives we create will continue to evolve, blending imagination with reality in ways that inspire and unite. The red planet's enduring appeal is also deeply philosophical. Mars challenges us to reconsider our place in the universe. It is a reminder of both our insignificance in the cosmic scale and our extraordinary capacity to shape our destiny. Standing on Mars, humanity will see Earth as a distant blue dot, fragile and unique, highlighting the importance of protecting our home even as we reach for the stars. As we explore Mars, we also explore ourselves, our limits, our potential, and our ability to adapt and thrive. The journey to Mars is a testament to the human spirit, driven by curiosity, creativity, and the desire to understand the unknown. It is a journey that transcends borders and generations, uniting us in the shared pursuit of knowledge and the dream of a better future. The enduring appeal of Mars lies in its ability to inspire. It is a planet that challenges us to think bigger, to push harder, and to dream beyond the boundaries of Earth. As humanity prepares to step onto its surface, Mars becomes more than a destination. It becomes a symbol of hope, resilience, and the boundless possibilities of exploration. The red planet is a reminder that no matter how vast the universe may be, our capacity to explore it is limited only by our imagination and determination. Mars will always be more than a planet. It is a story of wonder, discovery, and the relentless pursuit of knowledge. As humanity continues its journey to the stars, Mars will remain a beacon, guiding us toward the unknown and inspiring us to reach for the infinite.